actually. Huh? Yeah, yeah, that's right. Yeah. Thank you. Sorry? Ah, it's not though. It could be, but it's not. Yeah. Yeah, sure. It's actually 9:30. Yeah. Raghavan will tell you what is this.
Okay, I think it is time to start the first session. Uh, Good morning and welcome to the first session of this media meeting. It's a great pleasure for me to introduce the first speakers today, my colleague and my friend, Professor Sriram Ramaswamy, who is currently a J.C. Bose National Fellow and Honorary Professor in the Department of Physics, and he also has a visiting appointment at ICTS. Sriram is a highly distinguished theoretical physicist working in the general area of statistical physics. Did his bachelor's work at the University of Maryland, PhD work at the University of Chicago, and then did postdoctoral work at the University of Pennsylvania. After that, he joined IISc actually in 1983. So it's been like 86. I'm sorry about that. So it's been about 40 years. He has been here more or less throughout, except that in the middle he took a few years off to work as the director of the TIFR Center in Hyderabad. So he's of course a very well-known distinguished physicist, and his main area of research is statistical physics, or more specifically the dynamics of complex soft matter systems, and he has made very important micellar solutions, sedimenting suspensions, and so on and so forth. One thing I should mention specifically, during the last 15 years or so, he has been working in this area, which is now known as active matter, systems consisting of self-propelled objects. And he is one of the pioneers in this area. I mean, he can be recognized as one of the very few people who actually started working in this area and made fundamental contributions and played a very important role in the development of this subject, which has become very popular these days. So I'll just mention a few things about his honors and awards. Again, there is a big list, but I'll just mention a few. The Shanti Sarup Bhatnagar Prize, G.D. Birla Prize, and the Infosys Prize, among others that he has been honored with. He's a fellow of the Royal Society, the American Physical Society, and the three science academies in India. And very recently, just about a month ago, we are very happy to know that he was selected to be an international member of the US National Academy of Sciences. So it's been a great pleasure for me to actually have Sriram as a colleague and a friend. Benefited greatly from interaction with him, and so it is a great pleasure for me to introduce and we'll request Sriram to give his talk also in the area of active matter.
Thank you very much, Chandan, for that very kind introduction. I should also apologize for forcing Chandan to be a morning person just because of when my talk was scheduled. Chandan and I go back a long ways, one of my first friends in physics. So it's really a treat and a privilege to be introduced by him. Thank you very much for asking me to address the Academy. I'll be telling you. Oh, sorry, wrong. Which is? No, sorry. Is there a pointer? Oh, this is the pointer. Not seeing it. Oh, there it is. Okay, thanks. Yeah. Okay. Yeah. So that's the group. Oh, God, excuse me. Some of whose work I'll talk about, and some of whom I see are in the audience. And really, you know, essentially all my work is with these and these alumni from the group. I'll mention them individually wherever their work comes up. So I'll tell you the systems we're going to be talking about. You know, as this is supposed to be an overview talk to the academy, I'll tell you a little bit about old work also, and then talk about our current research. I realized a little late that I have to finish in 35 minutes, so I'll skip whole chunks of the talk altogether. So the kind of system we're talking about, as Chandan told you, is collections of particles, each of which is powered in some way. It could be the cells of a tissue, organisms in a group of organisms, subcellular power-consuming components like motors inside a cell, or artificial realizations like this thing that I'll say something about during the talk. And they can be operating in a variety of domains. They can be in a fluid medium, or they can be on a surface, and the dynamics becomes very different in these different cases, as you will see. And there's also interesting for those of you. Hopefully, there are some physics people in the audience, not from my line of physics, but others. There are interesting connections between active matter systems and very different driven quantum systems as well, which I won't have time to talk about, but which is all the more reason to pay attention to this field. I think I have to stand on this side. Yeah. My motivation for studying these problems, even though the origin of these systems comes from physics, come from biology, my motivation of studying these problems is that they present interesting questions in the fundamental physics of systems very far from thermal equilibrium. So, back fairly early in the game, I wrote a review which has proved to have some influence in the field, where I kind of made a manifesto where I said, look, we have to study this system. So the big hope is that we'll understand the fundamental laws governing the statistics of steady states, what phases you can have, what phases can coexist, how things relax. All the questions you ask about statistical and thermodynamic systems at equilibrium, we'd like to do the same kind of thing for these homogeneously driven systems in which each particle is taking up and converting free energy into systematic movement. And I've sort of made most of my living being able to write down descriptions of complicated systems without understanding their fine details very well, only keeping track of conservation laws and symmetries in the same spirit as you write down the equations of hydrodynamics without really knowing about molecules. So this has been, so I'll tell you some stories from this general endeavor. The subject is really interesting for another reason, which is that actually long before we got into the game, very distinguished fluid dynamicists had been worrying about this problem. And they wrote a beautiful paper, more than 50 years ago, which sank without a trace. Nobody really paid attention to it because somehow the theoretical machinery to do hydrodynamics for complicated systems was not yet available. But it's a beautiful paper and should be read, and it specifically says that the sorts of phenomena we're talking about should operate at the cellular level in living systems. So they anticipated actually several of the models that are now associated with other people in the field. All right, so the way this game has sort of many starts, one of which was a model attributed to Vicek because it was invented by a guy named Reynolds, in which you had agents trying to align with each other and which would undergo a phase transition from random motion to coherent motion if they aligned accurately enough and each of them had enough neighbors. And this is a bona fide phase transition. You can measure it in computer simulations, you can write down simple theories of its properties. And one of our entries into this field was to ask, well, you know, you've written this down in a rule-based way. What if it was taking place in a fluid? In that case, each agent trying to adjust its direction of motion would disturb the fluid in doing so because it has to change its momentum. How does that change? So we showed that it changes everything. The presence of a viscous fluid, what is this here? Keep losing the pointer. Yeah, that sort of cramps my style, but yeah. Yeah. That pointer is also gone. It was perfectly good a minute ago. Maybe if I'm on this side. It's just gone. It could be the battery, yeah. Is there a stick? Is it there? But anyway, yeah. Is there? Light is coming, but somehow it's not. Banta, okay, great. Okay, let's see. Right, it's there. So we showed basically that a fluid, the presence of a fluid completely changes things. Aligned states in a fluid, if the fluid is viscous, are basically unavoidably unstable. We then showed much more recently that if you take into account the inertia of the fluid, you can actually overcome this transition and you can have organized state, which kind of explains why you can have ordered flocks of large, fast organisms. This subject actually, this particular instability spawned a huge collection of experiments which were very exciting, which I won't have time to tell you about, and even led to predictions of, there it is again, of flow inside a cell, and this movie for some reason, maybe it will work if I restart it. Yeah, predicted that if you place a cell on a fixed geometry, the nucleus will start rotating. This is all kinds of fun and games, but this is very old work, and I'll just go on. Another bit of early work that has proved very influential is that if you have aligned states of things that aren't moving, these kinds of rods whose heads and tails are the same, they form states of the same type as you see in the crystalline displays, and they have little structural defects, some of which have a nose, and we predicted should therefore propel themselves in the direction of that nose. This idea again has turned out to be influential in problems related to developmental biology, to mound formation in cell cultures and so forth. That again is an ongoing story which has connections to problems as diverse as tissue growth, hydra regeneration, and so forth. Okay, now that's the end of the introduction. I'm not doing so badly. I'll come to our current research. There's one problem whose title is fun, but which I won't have time to go into, which I'll recommend you read about. I'll tell you about the physics of non-reciprocal interactions and their implications, and some rather odd mechanics of active chiral systems. Okay, non-reciprocal interactions is something we're all familiar with because human interactions are non-reciprocal, because affection isn't necessarily mutual. This sort of phenomenon takes place abundantly across the living world, not only in really sentient creatures, but even in much, in signaling interactions in cell biology and so forth. This type of interaction, what's important to realize about it, it is the hallmark of something out of equilibrium, because if you have a system at thermal equilibrium, the interactions of the system can be described as derived from a potential energy. If you have interactions from a potential, the force A exerts on B is minus the force B exerts on A. So it's strictly reciprocal. This problem is something that we've been playing with for a long time, but I'll tell you two manifestations of it in two rather different situations, both of which don't address biology directly. So one is sort of my favorite class of experiments that I've been engaging with in collaboration. Fantastic, thank you. initially in collaboration with Narayanan Menon, more recently with Ajay Sood. And it consists of a system in which you take macroscopic particles, half a centimeter long, and place them in a container like this, side view here, top view here. You vibrate the system up and down, and these particles walk. They do this. I can put on my glasses. So now some reason I can't find the cursor for activating the maybe this works. This is very strange. No, it'll be back. Just a moment. Let's see if I can now close out the slideshow and get my. Now it's back. Yeah. So this, you're looking at it from the top, and you're just vibrating something up and down. This particle, because of its shape and because of tilting slightly, is walking. I claim this is actually an honest recreation of self-propulsion, and we have chosen to study these particles as an example of active systems. In this system, what we did in our most recent work, mainly Roshan's PhD work with these other distinguished friends, is to study a collection of these kinds of particles amidst a collection of round particles which just sort of bump up and down and maybe diffuse. What does it like? It's like a collection of motile organisms or motile creatures in the midst of a collection of things that can be moved around but don't autonomously move themselves. And what you find is, as you increase the concentration of the background, keeping these motile agents the same, the system spontaneously organizes into these motile guys forming a row of particles all pointing the same way, which condense the non-motile guys in this manner. Rather more dramatically, I'll show you this movie if I can. Yeah. So this is low background concentration, higher background concentration, much higher. And what you should see is, in this region, these guys, and too short a movie. These motile particles organize themselves into two rows that condense this much non-motile material. Okay, so I hope that picture was clear. Here is a picture of the end state in a slightly different parameter range. These guys and these guys have created a kind of density phase separation. Dense phase here, low density phase here. Nothing about the interaction of these particles with each other makes them condense. They're just hard spheres. Yes? Sorry. Thank you. So these guys are condensed together only by the action of these agents at the boundary. Okay? The interesting thing is that you can do it in a slightly different geometry and get a similar but maybe even more dramatic phenomenon, which is, again, it's enough if you look at the last panel. You see a row, second panel, sorry. You can see one row of particles pushing a seemingly unbounded, bulldozing a seemingly unbounded row, sort of mass of non-motile particles in front of it. So it looks like you can create something that resembles vapor-liquid phase separation, actually in this case vapor-solid, a dense region, a rarefied region. The only agent that's creating this state is at the interface. When you normally have vapor condensing to liquid, it's because the molecules attract each other. Here nobody's attracting anybody. They're just being bulldozed into it. And the interesting thing is you get reproducible density contrast between the dense and rarefied phase. So it's not simply an accident of initial conditions or preparation history. So you get something resembling condensation in these systems. So it's a rather novel mechanism for attraction. So we were able to write down, I'll skip these things. The simple verbal qualitative theory is that the motile rods push the beads and create a density gradient. The motile rods have a shape, one end narrow, one end broad. Therefore, purely sterically, they are more easily accommodated in a region in which their nose sits in the high density end and their fat tail in the low density end. So, statistically, they are likely to be found disposed with the pointy end in a high density region and the broad end in a low density region, and their motion creates precisely that kind of density gradient. So, self-consistently, this feedback, this positive feedback creates a density gradient which is self-sustaining. It's important to note that this is actually what I was telling you about non-reciprocal interactions in the following sense. If you look at how the rod responds to a bead, the rod likes to point towards regions of high bead density. That means, in a sense, because it points and moves in the direction in which it points, it is as though the rods are attracted to the beads. It's not an actual attraction, but the rod movement is such as to make them move towards the beads. The beads are jostled and pushed by the rods. So, the beads are in effect repelled by the rods. So, this is not an interaction potential, it is an interaction rule emerging from the dynamics, which is precisely non-reciprocal for a childishly simple reason. So, one of the points I want to make is that non-reciprocal interactions are all the rage these days, but in fact the underlying physics can be sort of shockingly simple. Even though it's shockingly simple, its implications are very nice. You get this kind of phase separation. And you can write down, you can do something resembling grown-up physics and maths and write down continuity equations for the densities of the two species, say beads and rods. You can write down a purely diffusive part of the motion plus an active part. You can say if there is a rod polarization in a region, that will give rise to bead motion through the mechanism of pushing. If there is a and the rods themselves move themselves as well, and the rods like to point towards high bead density. You can write down a theory of this which will obligingly have, let me skip all this, an instability at high enough bead concentration and strong enough coupling of high enough tendency of rods to move the beads. It will have an instability of the uniform state with respect to phase condensation of the bead density. So, this theory qualitatively works nicely and has the right trends. You can augment it by going to developing things to higher orders and gradients and show that something resembling an interfacial tension also comes out of this, which I will not go into. You can also ask, how much bead material can one row of rods push? And you can again write down a theory of that based on the idea of a concentrated force density of these rods as they move along, and you can solve for the steady state of that problem. And what you'll, excuse me, it's going the wrong way. Yeah. What you will find is that the bead density, if you look if you ask for the bead density in the direction which is being pushed, it has a decay length whose scale is set by how hard it is to compress the beads. So, the more packed the beads are, the longer a batch of beads you can push. So, in some sense, there's no limit to how much bead material can be pushed by the rods, because this whole mechanism doesn't use the mass, doesn't use inertia in any way. It just uses the kind of pushing that you use to move stuff, heavy material on a floor. So, in effect, it suggests that you could get macroscopic phase separation with a sub-macroscopic quantity of separating agent. We don't know for sure if this is 100% right, but it's tantalizing and we're working on it. Okay, just a few months ago I was giving a talk on this, and one of my friends in the audience said, this looks an awful lot like something that we've been working on. It turns out they've been working on two species of motor proteins, and both of which walk on microtubules in opposite directions in a classic motility assay. The only difference is it's a two-component, two motor species motility assay. And what they find is what is referred to in this trade as microphase separation. That is, you get regions rich in one motor protein, regions rich in another motor protein, separated by rows of microtubules. The difference between this system and ours is primarily that you don't get two sort of seemingly unbounded domains, you get stripes of A, stripes of B. But the mechanism is similar in a symmetry sense. The difference is, in our case, the rod-like objects are the motile agents, the medium, the beads are non-motile. Here the motility is not in the extended object. But if you write down, if you stare at the equations, you realize they're very, very similar. So there is, so again, I want to emphasize the importance of doing physics in the way we do it, because you work on a problem on sort of general grounds, looking for generic, non-specific mechanisms, and typically they turn out, they appear even in the living world. And this is a nice example, I think. Okay, let me tell you. How much time do I have? There must be a thing somewhere. Huh? Ah, good. Including questions. 15. Okay, great. Okay, so let me turn to a completely different non-reciprocal interaction problem. There are models of magnetism in which you have a lattice, and at each side of the lattice you have what you can think of as a little magnetic moment. Okay, there are some models in which that moment is just this way or that way, two-state. There are other models in which that moment is a two-component vector, others in which it's a three-component vector, and so forth. That depends on the symmetry of the magnet in question. Okay, planar spins are a popular problem. So these are two-dimensional vectors, and the problem of greatest interest is two-component vectors on a two-dimensional lattice. This is a famous problem for lots of physics reasons, having to do with topological order and so forth. But the idea is the following. You've got these agents. In a dynamical description, the angle of each of these agents tries to line up with the angle of the neighboring guys through an interaction matrix, Jij, which connects site I to site j. And in all the models we look at here, Jij will connect only nearest neighbors. In the classic models, this Jij is a constant matrix, say +1 or -1 for nearest neighbors and 0 otherwise. Okay? But we got interested in the question of what would happen if the way this vector aligns with its neighboring vector depends on how this vector is pointing with respect to the line, with respect to the bond joining it to its neighboring vector. Now, why would that happen? You can imagine that happening if the interaction wasn't coming from a pair potential, but instead from a signaling interaction. So you've got some kind of antenna or receptor, and you're pointing in a certain direction. Okay? So then you are likely to pick up the signal from that guy. So if there's something being exchanged, then this kind of interaction where the Jij depends on the angle between which way you are pointing and the vector joining you to a neighbor is a totally reasonable thing to look at. So we started playing with this model. This is Pankaj Popli, a postdoc in the group. I should also point out that these planar spin models are closely related to physics-based models that people write down for planar cell polarity. In those models, this non-reciprocal aspect is not routinely taken into account, and I wonder why. I've, with some friends, some of whom, at least one of whom is in this building, we've looked a little bit at these kinds of models recently. Let me skip this algebra. The problem of interest is, so what you can do is you can take this, wrong. You can take this dynamics and take a continuum view of it. Don't look at it on a lattice. Look at scales much bigger than the lattice spacing and write down a continuous partial differential equation for the orientation field. And I'll skip the algebra, but if you do a sort of rough and ready continuum limit, what you find is up to second order in gradients, it becomes the equation for a unit vector p, which relaxes by trying to line up with its nearest neighbors in a kind of isotropic way, and in addition has this term which says that if there is a local inhomogeneity in the alignment, the orientation will itself transport it. That is, if at t equals 0, things are kind of largely aligned, but this region has some misalignment. the local mean orientation will transport this misalignment elsewhere. Now, this is very interesting because P is actually not a velocity. It's just which way a given rotor is pointing on a lattice. The signaling type of interaction that we've put in makes P act like a velocity. This term again cannot be derived as a derivative of a potential. It makes the P field act like a velocity field. It becomes an equation known as the Toner-2 equation without what that equation normally contains the density field. There's no mass transport anywhere. There's no agents moving from one place to another, and yet orientational information transports itself in a directional way. This equation, when augmented with noise, when you include noise, is known to have what is called long-range order in 2 dimensions, which means that if a given vector is pointing this way at low temperatures, the probability that infinitely far away one of the vectors will be pointing the same way is non-zero. That's called long-range order. The same model, if you didn't have this term, is known not to have long-range order, but to have what is called quasi-long-range order, in which in the low temperature phase, without this term, the orientation is highly correlated. The total amount of order on infinite scales is 0, but if I am pointing this way, the probability that a distance r away, somebody else is pointing the same way, goes down very slowly, only as an inverse power of r. And Kosterlitz and Thaler showed that there is this miraculous quasi-long-range ordered phase which has these properties. So what Toner and Tu had shown is that the presence of this term gives you a long-range order. So our question is, have we found a lattice model in which whose non-reciprocal interaction gives you long-range order through the Toner-2 mechanism? It's a very nerdy physics question. There's some prettier, purely qualitative other physics which I'll show you in a little while. So what we did was to investigate, the true meaning of the continuum limit in this model. And what we did was to, excuse me again, I'm bad with this. We studied both the nature of order and vortex interactions, which I'll tell you a little bit about. First, let's study the nature of order. The diagnostic of that is to look at the angle fluctuations on larger and larger length scales. One way to do that is to write the angle field in terms of its spatial Fourier components, that is to say as a function of wave vector, which is 2 pi over wavelength with a direction, and look at how the variance of the angle field as a function of wave vector changes as you go to longer and longer wavelengths, that is smaller and smaller wave vector. If that angle field was the angle field of a system that has spontaneously picked one out of a continuum of directions with no lattice bias, then what you should find is that this angle variance as a function of wave vector, wave number, should go down as a power. This is a log-log plot, so a straight line is a power. And so tantalizingly, we seem to see a power law. This is for wave vector perpendicular to the ordering direction, this is parallel to it. But what we see is that at the smallest wave numbers, the largest scales, the angle variance becomes finite. That the angle variance becomes finite is a dead giveaway that actually the angle, the orientation is anchoring to the lattice directions. So what that means, again, as I said, it's a fairly technical point, is that this rule where you anchor to the lattice directions is inescapable no matter how large a length scale you go to. The angle fluctuations don't wipe out the trace of the presence of a lattice. So there was a bunch of recent work which was quite confused in this regard, and one of the roles of this particular piece of work is simply to clarify what's actually happening. In field theory terms, the angle field gets a mass, okay? So the way to take, so the continuum limit for these fluctuating spin models is tricky. You have to take the statistical continuum limit, shows you the angle field actually has a mass. So if you want this model to create long-range order without lattice artifacts, you have to sort of shuffle the interactions at the unit cell scale in such a way that you don't, and then you can do it. Sorry, again. Another fun and games thing in this problem is topological defects. So what do I mean by those? I mean, here, for instance, is an orientational configuration in which the vector is pointing inward everywhere around a given point. So if you go around this point, as you go around by 2 pi, the orientation also goes around by 2 pi. Okay? And that's something you can't remove. If you had just one of those, you can't remove it unless you change the boundary conditions at infinity. It's topological. Two such objects are known to interact with a potential that depends logarithmically on scale. Their entropy depends logarithmically on scale, and therefore you can ask about a phase transition as you change temperature, and that's what Kosterlitz and Thouless did. The question is, what happens to that phenomenon in this problem? It turns out that even if you're at very low noise, where the vortices should rebind and the system should stay ordered, if you prepare a pair of vortices, plus sign and minus sign, in this manner, what you find is that at large enough scales, they get cloaked from each other. Let's see if this movie works. So here's a plus and a minus at very low noises. If it weren't for that self-advection, these guys would find each other and annihilate, and you get a perfectly ordered phase. What we show is that the presence of that advection smears the field of this vortex in such a way that this guy basically doesn't see this guy. There's a weird kind of vortex shielding. And the result, depending on the relative orientation of these guys with respect to the background orientation, is that it gives time for new defects to be nucleated. And eventually for a kind of eruption of defects. If you wait for it, it should happen. So even at very low noises, eventually the fact that a stray pair of defects get nucleated, because they don't annihilate, more and more defects get nucleated, and finally the phase destroys itself for essentially for arbitrarily small values of that non-reciprocity. So this is closely connected to findings by Hugues Chatet and group a few years ago, directly studying the stochastic PDE of the problem. Okay, one major insight is whether a pair of defects initially put in with a certain separation annihilate each other or hang about forever turns out to depend on a length scale which is governed by the ratio, is governed essentially by the degree of non-reciprocity. So if you look at the equations of motion, you see that this has two gradients, that has one gradient. So the ratio of J to A is a length. That length gets bigger and bigger the smaller you make non-reciprocity. So for any amount of non-reciprocity, there should be a length such that if you put in the two defects farther apart than that length, chances are they should be shielded from each other. And this indeed is what we find. This is the locus of points in the initial separation non-reciprocity plane, such that basically for a given level of non-reciprocity, if you separate the pair initially by a large enough amount, for all practical purposes they fail to annihilate. That makes time for nucleation, that makes time for the phase to be destroyed. So yeah, you can read about this where? Here, the paper by Pankaj, Ananya Maitra and me. There are interesting connections to other different problems that we've been studying in magnets with another student, Nisarg Anjurito Mukherjee, which will come out soon. Okay, let me come to the, how much time? Only 2 minutes, okay. So maybe realistically, I'll just tell you very briefly. We looked at a very different class of systems, active systems with positional order, either layers or columns. Or I'll tell you mostly about columns. So if you have a system with columnar order, chirality, and internal energy dissipation creating active forces, which speculatively could describe some of the physics inside highly ordered columnar structures such as the axon, we predicted that the mechanics of an array of columns of that sort without mechanical inertia can have oscillatory dynamics, so for example, if you could say an in-plane shear of this sort, simple shear produces pure shear, shear produces simple. These things beat against each other and give you oscillations. And this is oscillations without mechanical inertia. I will not try to explain the physics of that, but instead I'll stop and take questions after just a couple of things. One is my summary, never mind it. There's lots and lots of challenges in this field, including inertia, finding experimental systems with inertia, finding systems which you can control the motion of active matter, including information processing in theories of active systems, including evolutionary processes. And the overall outlook includes many open questions that I just leave you with. So I think I'll stop there and let you ask questions if you have any. I guess I've pretty much run out of time. I'm actually out of time, right? Oh, there is. Okay. Yeah. So, okay, I can make two statements of quantum clocking. One is people have taken sort of what are they called? Tight binding models of particles hopping, and introduced a spin variable which also dictates which way they hop. So you have a two-state variable which, rather than just being a spin angular momentum, is actually dictating which way the particles go. There are things about those models we don't understand, and they've sort of modified the dynamics using a what's the Bath? Lindblad, that type of, yeah. They've used sort of quantum stochastic dynamics out of equilibrium to claim that you can get one-dimensional flocking order in these models and so forth. It's not very clear what's going on there. We've been looking very hard at it. Even the classical limit of those models is rather weird. There's something with Chandan, Subrato, Narayan back there we are looking at. We have results in part we don't understand. The other point about quantum active matter is, in general, if you take a 2D quantum system, let us say the interface between two bulk leads at different chemical potential, that 2D system is in effect governed by some kind of active matter dynamics. Examples of that include two DEGs subjected to microwave, Ramesh Mani's work. So there are systems which, on general symmetry grounds, have to correspond to this class of models. Yeah.
So in the systems you talked about initially, these were, there was spherical media, if I understood, and rods.
Right.
But in a cell, you'll have all kinds of different shapes.
Right.
And many different. So will this damp out these effects, or what?
No, the point is, if you've got 4-aft asymmetric polarized objects and they're out of equilibrium, generically they're going to be motile, even if they don't actually have appendages or whatever it is. There's a variety of ways in which it moves. So the other thing is, the degree to which it damps out will also depend on adhesion and other processes. But adhesion is also usually what confers motility on some of these things. I mean, differential adhesion and then, focal, release from the back, moving forward. So it's not necessarily that mere heterogeneity of shape will kill everything. It becomes a question really of looking for a clean experimental system. Basically, what we offer in that first part of the thing is a fairly novel mechanism for phase separation, not using attraction but using motility. And at least one example that seems to look like it is there in the motility assay literature. That's the only statement I'll make with confidence. Right. So ordinary motility by itself can give you phase separation. If you have particles that are moving and take time to change their direction of motion, then if they start moving, like in a stampede or a melee, things can get condensed. And if more stuff comes in before these guys have to turn around, the objective criterion for which basically is if the packing fraction times what is called a Peclet number, which is the speed times the persistence time divided by the particle size. If that dimensionless figure of merit is large enough, you will get condensation, again for reasons of motility and not attraction. So that idea seems to be important in liquid-liquid phase separation and phenomena of that sort. This is not that far from that. Here the big difference is the entire phase separating agency is only on the edge, and it looks like an edge can completely alter the physics of a bulk if we're not too far. Yeah.
First of all, thank you for delivering such a great lecture. I really enjoyed your talk. I'm coming from outside the field, but I can see that especially your self-propagating elongated particle, because of asymmetry, seems to have a lot of application in medical science, as you said. So are you trying to like work with medical researchers and trying to see what kind of implications it can
Okay,
have?
I'll tell you the honest answer to that is no, but I am collaborating with Ambarish Ghosh, who does that kind of physics.
Okay.
We have a student jointly, Karan Priya, who's just beginning her work. Those are magnetically driven systems, but you could have others.
But can you tell in a couple of sentences what kind of you're thinking of applications?
I would honestly say that I didn't think of any of the applications. In Ambarish's specific work, you want to deliver something to a particular site in a guided way. There are a variety of ways of doing it. I don't want to speak for him, but yeah.
Okay.
Yeah.
Thank you.
But there's it's a more, the point is, given that these particles not only move but can also move other stuff, you can imagine delivering cargo in directed ways. That's one example.
Right.
We also have other theoretical examples of particles where the motility mechanism is not this vibration, but this again has a connection to this institute in the sense that Ayushman Sen studied particles with half coated with a catalyst, immersed in a medium containing a compound that catalyst breaks down. Those objects become self-propelled also. And then you can ask, can those objects do things like chemotaxis because they can respond to gradients? So we've done some work on those problems as well.
Very interesting. Thank you.
Thank you very much.
Let's thank Professor Chandan Dasgupta for chairing the session. Now we move on to the next session. And I'm standing in for Professor Mustaswamy, who could not be here today. So this session has two talks by fellows and associates. And the first talk is by Dr. Gautam Bharali of IISc Bangalore on the role of geometric coefficients in a problem in control theory.
So the duration of the talk is 15 minutes.
15, 20 minutes.
20, inclusive of question and answers.
15 plus 5.
Yes. And I get a warning at 10, right?
15.
Does the Academy still do that?
15.
So this is the pointer.
Ooh, wow.
Good morning, everybody. I'd like to begin by thanking the Academy to give me an opportunity to address this very illustrious audience. I'm going to present a very short account of some work I have done a few years ago. And I'm going to start by presenting an extremely sharp mathematical question. So this first slide is a very, very sharp, very precise mathematical problem. So you consider this parameter n, a positive integer n greater than or equal to 2. So this Cn times n is my symbol for the space of all complex n by n matrices. And so that's a linear space, and let E be a linear subspace thereof. And I'm going to write down a certain functional. The actual formula is not relevant over here. The only thing that I want to point out is the presence of this reciprocal here. This presence of this inverse shows us that this functional has a property, one of the properties of a standard norm on a vector space, namely if you scale this matrix A by a complex number, then the absolute, so if I scale this matrix A by a complex number C, the absolute value of C is going to come out. So this object is called a structured singular value. And because a mu sub E has at least one of the properties of a norm, we can talk about the unit quote-unquote norm ball with respect to mu, which I'm going to call omega sub, whoops, what did I do? What did I actually do? Right. So we can talk about the so-called unit ball with respect to this norm, which is the set of all n by n matrices such that mu sub E of that matrix is strictly smaller than 1. So this is a sharp problem. You are given m distinct points, zeta 1 through zeta n in the open unit disk, and you're given m matrices W1 through Wm coming from this ball, not necessarily distinct. And the question is, can you find either necessary conditions or sufficient conditions, ideally necessary and sufficient, on this data such that there exists a holomorphic interpolant, which means there is a holomorphic map from the open unit disk into this ball such that the jth zeta is mapped to the jth matrix. So for non-mathematicians in the audience, well, this is just a juicy enough problem in of itself. We are puzzle solvers, and this problem doesn't need any other justification, but there is actually a context to this problem. So we look at what are known as linear input-output networks. So this is a schematic of such a network. This is a network of interconnected devices with the property that the device outputs depend linearly on the device input. So these are called LILO networks, linear input, linear output networks. And the problem is to, given a network, to design a controller that's going to stabilize this network so that given some sort of a feed, the network is not going to respond unstably and have the output blow up. I'll very soon talk about an example, a concrete example of the sort of stabilization that we need. So the E is going to be the vector space of all parameters that govern a LILO network whose parameter values are uncertain. So you see, this is a real-life problem. The system parameters are not going to be frozen at some ideal value. There's going to be some amount of noise. And in fact, the reason for wanting to stabilize a LILO network is because given a deterministic feed, a network may behave extremely unstably because of noise in the system parameters. So the key towards first even understanding if there exists a controller given a particular network design comes from the work of Jim Helton. And this is sort of the mathematical analysis of the worst case situation, which is that the vector space of parameters is exactly Cn times n. So in this worst case assumption, a LILO admits a controller that stabilizes the network only if an associated interpolation problem into omega sub E admits a rational interpolant. So in this case, in the language of the first slide, E is actually Cn times n, in which case if you do the algebra, the structured singular value is just the familiar operator norm for matrices. So this is the operator norm unit ball. So notice how, so this is not if and only if, right? So you have a controller that stabilizes the given network provided this admits a rational interpolant. which means that if this problem does not admit a rational interpolant, then you have no conclusion. And from safety considerations, therefore, engineers are simply going to trash a particular network design if this interpolation is not does not admit a rational interpolant. So in other words, a possibly very sound design is going to have to be trashed. And the issue over here is that for this given problem, it is extremely difficult in general, given a data set, to have a rational interpolant. I'm going to talk a little bit more about that in the next slide. But then, think about this. So let me now give you an example of this sort of a network. So this is a problem. When one is prospecting for oil, typically one is going to have to drill for thousands of meters of depth. So our network is simply the drill shaft, which has a drill bit at the end of it. And you'd need to, this shaft is so long that you'd have to stabilize the shaft. Because imagine if the shaft actually buckled horizontally, the consequences would be disastrous. But now think, why on earth would I care about noise in the system parameters in the up-down direction? That least matters, right? It's, so of the vector space of parameters, we don't care about many of the about uncertainties in various in many of the parameters. And that might probably be a way out of this issue over here, moving away from the worst case analysis of a proposed network design. And the big breakthrough over here was Jim Doyle. The object that I described in the first slide was introduced by Jim Doyle, who in fact proved an analog of this theorem for mu sub e, where e is strictly smaller than Cn by n. All right. So if you had the worst case scenario, then in fact the analysis of the problem in the first slide is completely understood. And for the experts in the audience, even in the case n equal to 1, we sort of see, so this is the Pick interpolation problem. If I just had 2 points, 2 distinct points in the unit disk, and 2 target points in the same unit disk. Schwartz's lemma will tell you that in many, many cases, we would not find a rational interpolant, and that's at the root of the problem I had mentioned in the previous slide. Now, at the opposite end of the spectrum is the case where this E is simply the space of all diagonal matrices. So this is a toy case. In this case, the unit ball turns out to be, in fact, the set of all matrices of spectral radius less than 1. And this immediately creates all kinds of pretty nasty problems with the analysis of a diagnostic of whether there is a stabilizer for a network where the parameter uncertainties we care about are captured by this space. And one of the problems is that this ball is unbounded, and more than that, it doesn't even have a bounded realization under any holomorphic coordinate change. So what this means is, for the experts here, there's no Montel theorem. So if I had to build an iterative scheme, if I had to write down an iterative scheme to build a rational interpolant, the point is we wouldn't know whether such a scheme would even converge. So the other problem is that what makes the analysis of the problem on the very first slide such a roaring success in the worst case scenario is a facility that we don't have for this ball. And technically speaking, the group of holomorphic automorphisms on this quote-unquote unit ball does not act transitively. Let's say, less technical language, what that means is I cannot, unlike in the worst case scenario, write down a closed form diagnostic for whether or not my network is stabilizable, despite the theorem by Jim Helton that I hinted at. So here's a strategy, and this is a strategy pioneered by Agler and Young, independently by Constantin Kostara, and the strategy is the identification of a domain sitting in C, and now compare the dimensions of Cn cross n. This is the dimension of the space of matrices, and this object. The formulas are not important here. What Agler and Young demonstrated is that if the data given for me in that original problem is well-conditioned, I'm not going to talk about what well-conditioned means, because those of you who work on simulation know philosophically what the idea is, and the actual description of what well-conditioned means in this situation is not relevant to this talk. So for all data that are well-conditioned, the matricial data will admit an interpolant if and only if this auxiliary data set that can be exactly computed given the original data admits an interpolant into this thing called the symmetrized polydisk. And the enormous advantage over here is that this is a bounded domain. So we can write down successive approximation routines to check whether or not there is a rational interpolant. And this is actually kind of efficient because you don't have the curse of dimensionality. The dimension of this is significantly smaller than the dimensionality of the original problem. So I'm going to have to skip. I had written up some stuff for the experts. I'm going to have to skip this in the interest of time. But the E that I had talked about in the previous slide, it's really a toy case. It's a proof of concept, but it's quite impractical. It's been shown by Doyle and Packard that the more practical instances of the space E that I had talked about in slide number 2 are of this form. So block diagonal matrices. Unfortunately, when you write down omega sub E associated to this, the same problems as described in the previous slide occur. Any strategy of successive approximation of a possible rational interpolant is confounded. And also you have this terrible problem of dimensionality. So I had a few sentences for the experts over here, and I'm just going to read out one line. An alternative to understanding how that object G sub n arose in Kostara's work is to actually realize that the general linear group acts on omega sub n in the previous slide by conjugation. And in fact, this Lie group also acts by the conjugation action on the associated omega sub E that I haven't written down here, but whose formula I have given. So it turns out that the G sub n is the GIT quotient. That's the warning bell. I think it's the GIT quotient of the conjugation action of the general linear group on Cn by n. And so the core of the result I'm going to finish up with is that I'm going to introduce a domain that I call a quotient that simply happens to be the GIT quotient of Cn by n with respect to the action of this Lie group. So I'm going to wind up with my final slide. And the theorem is this. I mean, there's lots, but let's look at a sample. Let's look at E of this form. The main theorem basically says this. omega 1 sub n is the omega sub e associated with this. And what this theorem says is it identifies precisely the locus of ill-conditioned matrices for the stabilization problem with omega sub e associated to this e. And this locus is explicitly given by this formula. And moreover, it's a very explicit formula, and it's extremely easy to algorithmically determine, if I give you matricial data, which of these matricial data are ill-conditioned. Moreover, the locus of ill-conditioned matrices is really, really tiny inside this ball. There is this GIT quotient. Its dimension happens to be 2n minus 1, which again is significantly smaller than n square and more significantly smaller as n increases, which is what happens in practical problems. So you do have a handle on the curse of dimensionality. And an analog of the theorem in the previous slide was, if I have these distinct points in the open unit disk, I have these M matrices in the outside of the locus of ill-conditioned matrices, not necessarily distinct, then the existence of a holomorphic interpolant for the problem that I care about is the holomorphic interpolant that I care about exists if and only if there exists a holomorphic map from D into this domain, which has all of the properties that facilitates the search for an actual construction of a rational interpolant, satisfying this auxiliary interpolation problem. And once again, the data, given the data, the auxiliary data can be very explicitly and very rapidly computed. So that's sort of the summary of this main result, and I'll stop right here. Thank you very much.
Thank you, Dr. Berali. Are there any questions or comments?
Gautam, if you go back to very early in the talk where you had an only if result, I was very confused when you said that you seemed to assert the contrapositive of it and say that that wasn't true. So I missed something clearly.
No, in fact, I was in fact a little careful about this. So what I had said was, you're absolutely right. So the existence of a rational interpolant implies the stabilizability of the network. Converse is not true. However, if we know that there is no rational interpolant, so there's nothing I can conclude, right?
Okay, but that's not, okay, I'll quibble with you later.
Okay, so, but do you agree with me that
No, you said only if, that means
yes.
this implies that. It doesn't
Beg your
mean
pardon?
that implies. A only if B means that
yeah,
A implies B.
No, A only if B means B implies A.
I'm just not.
Okay, all right.
Apologies.
Okay.
Any other questions? If not, let's thank Dr. Berali for his interesting presentation. Now we move on to the next talk. It's by Dr. Udita Uday Ghosh from IIT BHU Varanasi. And the talk is on complex fluids behavior at the interface beyond the trivialities.
Hello. Yeah, am I audible, I hope? Yeah, okay. So I'm Udita. I would first of all like to thank the Academy for giving me this opportunity to speak to such a diverse audience. And also, luck meeting yesterday at the dinner made me realize one of the senior fellows told me that we will have people from the bio background. So what I'm going to do is, I'm a trained chemical engineer, but I will try to bring in some of the flavor from different domains while I'm discussing my talk. So So briefly first, what are complex fluids? So complex fluids essentially imply that you have an internal microstructure. That microstructure influences the flow behavior of that fluid. So somewhere they lie between solids and liquids, carrying both the characteristics. The characteristic they borrow from solid is that they'll have a microstructure which evolves with time with respect to the flow fields it's exposed to, and that in turn influences the macroscopic flow phenomena that we are seeing. So I'm going to talk about different kinds of complex fluids and how they behave at the interface. So moving on, these are some of the examples. So if I start with the first one, this is something I'll talk in detail. So what you can see over here is a fluid filled into a tumbler and it's rising onto a rod. So this is what will be the first topic. Second over here are your cilia present in the lungs. So we all know that the mucus that's present, the cilia tries to beat around say 60 hertz, and the mucus is an extremely viscous fluid. But as a rheologist, for me it's also elastic. So if I create any perturbation, it will try to revert back to its original form when I remove the perturbation. So the next one is some of the spermatozoa. The first one here is talking of a spermatozoa swimming in a Newtonian fluid. So what's a Newtonian fluid? If I apply some stress, it will react linearly in response to that stress. Whereas any fluid that deviates from that linearity becomes a complex fluid. For example, here you can see a viscoelastic fluid. So if the spermatozoa is moving in a Newtonian fluid, the waveform it carries is somewhat sinusoidal, which becomes hyperextended when I move to a viscoelastic fluid. So these are some of the inspirations that lead us to study this domain. The next one is something which Professor Ramaswamy has already discussed. So you basically have a nematode, a C. elegans, and here it is allowed to move in a monodispersed mixture. You can see a different kind of waveform, whereas if I make it polydispersed, its velocity profile also changes. So essentially what we are trying to say is that if I change the flow behavior, I can do it both ways. Either the organism can influence its environment or the environment can influence the organism. So mathematically speaking, I can measure few parameters. I can measure how fast or how slow the fluid relaxes. So that's my stress relaxation modulus. I can measure its viscosity. Now please note over here, if it's a Newtonian fluid, this viscosity will remain constant with respect to the applied shear rate. But since we are talking of non-Newtonian fluids, now it can change with shear stress, it can change with shear rate, and it can also change with time. Just to give a small example, the toothpaste that we use starts to flow when you apply a certain amount of stress. So that's a complex fluid. You give some stress, it yields, that means it starts to flow. So moving on. So what happens is we go back in the year 1940s. So there is this person called Weisenberg. He sets up a small experiment. He takes tumblers, fills them with fluids, plugs in a rod and starts to rotate them at different RPM. What he sees in the first kind is here a simple vortex is seen, just like if you take water and you're stirring it with spoon. Then he sees there are some fluids, which he calls abnormal behavior, start to climb onto the rod. So this effect comes to be named after him, and this is called as your Weisenberg effect. So it's nothing but when a fluid which is rotated starts to climb onto the rotating rod, something you have seen in milk, cake batters, bread dough and so on. So the question is, why does it happen and what can we do? Say if I dip this rod into a pool of oil, will it climb less? Will it climb at a lower speed? So these are two of the questions that we started to look in. So we have made a very simple setup. We are just going to replicate what Weisenberg did. The only difference will be that I will dip my rod into oil and repeat the experiment. So I'm not sure if the videos are running. So what you see on the left is a bare rod running at 200 RPM, and on the right it's an oil coated rod at 200 RPM. I'll just increase it, make it 600. So if you notice over here, there are two major things that are happening. First thing is that we see the rotation starts at a lesser RPM when it's an oil dip rod. So that means there exists a threshold value at which the fluid will start to climb on the rod. And when I dip it in oil, this threshold value decreases, as well as the height to which the fluid climb also increases. So speaking simply, there are two players in this phenomena. One is your centrifugal force, which is allowing the fluid or asking the fluid to move towards outside the center, towards the bulk, whereas it is getting opposed by what we call as the normal stress differences, which become non-zero in this case. So to explain it, I will just move ahead and I'll show you maybe a very simpler form. So if you find out the viscosity of such a fluid, you see that it starts to shear thin. So you find that it starts to shear thin, which means its viscosity is decreasing with respect to the applied shear rate. Not only that, it has a non-zero storage modulus. So whenever the fluid will start to get thrown outside, the internal stresses, which means the normal stress differences, will try to pull it inside, which causes it to rise up to the rod. How do we model this? So we pick up what is called as the Gesichus model. I will not get into the details of it, but the key player I was talking of is over here. So the stresses in your theta and r direction, if you take the differences, these are no longer zero. If I talk of water, if I replace the same polymer by water, these were zero. So that's why you were getting a vortex. So we have started to model this, and what we see over here is these are very similar to what happens when you take a polymer. It will go, or if you are rotating a spaghetti, what does it do? It will try to stretch and reorient. So the same thing is going on with the polymer molecules. They are really long chain molecules, so they are trying to climb, opposing the centrifugal force. So we have tried to map this using a really complicated equations which has these three parameters. So here we have a stress relaxation time, how fast it relaxes after being exposed to a perturbation. We have a mobility parameter, which is used as a tuning parameter, and you also have a contribution from the polymer, which goes into its viscosity. Now the question is, what happens when it's an oil dipped rod? So in case of an oil dipped rod, it starts to slip at the rod, which means the contact line will now get deepened. So to quantify that, you need a contact angle which is at the rod fluid interface. So we have simply incorporated that into the slides, like into our model, which you see over here. So cot theta I and cot theta naught, these are just the contact angles. And we find really good matches with our experimental data. So you can clearly see here that in case of a bare rod, the contact line remains pinned, whereas if I talk of an oil coated rod, it starts to slip at the rod fluid interface. So I'm just going to skip this. So this is our match, what we find out theoretically, and there are a couple of takeaways. The first thing is that we have a threshold value. The second is the oily rod decreases the threshold value, and it also increases the height to which it can climb. In the interest of time, I'll just move ahead and show where this is being applied. So you can see over here that this can be used to create micro patterns. What we have done is, like what this group has done, they've just connected a steel capillary to it. So now the polymer will start to produce threads, so you can actually generate any kind of patterns or fibers. So we can have some microfibers over here. So if we are talking of this, we have simply reduced the length scale. So instead of using a rod of 1 millimeter length scale, we reduce it to 3 orders, go off to the micron scale, and we can generate such micro patterns easily. So what are the advantages? You can transport high viscosity fluids. You can use them to create desired structures. And if you apply electric field, then the applied voltage also permits you to reduce the diameter to your requirement. So these have been used to create some of these fibers as well. So with this, I will move on to the next phenomena that we are studying in our group. So these are some of the diagnostic devices which are usually based on papers So we decided to take this up and figure out what happens if we use actual fluids. So the biological fluids are closer to polymeric solutions instead of Newtonian fluids like water. So to study this, we are now moving on, and okay, I'm just going to skip the math. If you want, yeah. So basically this is Lucas-Washburn model. What it assumes is you take a bundle of pipes and you're studying how the fluid rises through it. So that's called the capillary rise. Same thing what happens when you dip a straw into a cup of water. He says that the length or the height to which the fluid can climb is proportional to some exponent which is p. According to Lucas, it was 0.5. So if viscosity dominates, it becomes 0.5. If gravity dominates, it's 0.33, and if inertia dominates, then it's 1. So the whole story lies in this exponent p. So we ask the question that what happens if instead of a Newtonian fluid, we replace it with a polymer. So do we get a single exponent? Does it stay for the entire phenomena, or does it stay for in parts? So we are talking of non-locality over here. So again, single temporal length scale, will it work or not? So to find out, we have taken Whatman grade filter papers. These are different grades, so they signify different pore diameters. The pore diameters are listed over here. Of course, you can see it's a very complicated labyrinth structures. So these are cellulosic fibers. So the question of swelling of these fibers will also come in question. So what we are going to do here is set up a capillary rise experiment, do it with polymeric solutions, which is polyethylene oxide, for different concentrations. Keep in mind the viscosity changes with the applied stress. So this is how the viscosity looks like, and I'll just show you some experiments that we have done. So we've just put in a food dye to track how the fluid moves up. So if you see over here, you'll find that the fluid, the polymeric fluid, takes a really long time to rise through the strip. So that means there is a delay in the rise or the capillary rise compared to water. So the question is, why does it happen? So first thing that we need to note is this kind of a delay is seen only beyond the critical concentration of the polymer. It does not happen before it. So we went on to investigate it, and we figured that there are actually two regimes. The first regime we couldn't quantify because this happens really fast, so that's the inertial regime. The second one follows the Lucas-Washburn. So we have viscosity dominating over capillary forces, but as we move on, we find a gravity dominated regime at the longer time scales. So this, interestingly, these two regimes were not reported for polymeric solutions. So that means a single exponent will no longer work. Surprisingly, this stays for most of the polymeric concentrations beyond the critical one, which is 10 to the power minus 5. So some of the other things that we are trying to track is what happens if we talk of the front, the actual front. So you find the difference in color intensity. This arises from the saturation of the paper substrate. So the lighter and the darker front can be distinguished, and they are called as the pre-wetting front and the wetting front. In case of polymeric solutions, we find that these follow very closely, although the morphology is extremely corrugated in case of water, which smoothens out in case of polymeric solutions. So these are some of the major takeaways that we had. Mainly the exponent that changes from long time scale gravity dominated in case of Newtonian fluids to the existing of two scales, that is a viscosity dominated followed by gravity dominated in case of polymeric solutions. Now the third thing that I wanted to highlight is the coalescence of droplets. So coalescence of droplets has been studied by chemical engineers, mechanical engineers, but there exists a direct analog in case of biological sciences. So what we see over here is basically your mouse embryonic cells, and they are getting aggregated. So considering this, if we try to replicate such systems, not the exact thing, but we try to do it using aqueous cornstarch suspensions, which technically speaking are shear thickening fluids. So now the viscosity will increase with the applied shear rate. So I will just go ahead with the final thing. So we have just taken a configuration which is called as a sessile pendant. So I will have one drop placed on the substrate and bring in another one from the top. Try to figure out how the neck evolves between the two droplets with respect to time, and repeat the same experiment for different concentrations of cornstarch. So if I go and show you so this is recorded at a very high FPS because it's difficult to capture the initial point of contact. So what you see over here is a delay in case of increasing the solute concentration, and these results match with one of the PRL results by Roish et al., where it has been stated that jamming is possible in case of such high concentration. So this is the main takeaway of our study. We find that in case of these cornstarch suspensions, there is a critical volume fraction below which it shows Newtonian coalescence. In simple words, the neck radius varies as 0.5 times to the power times of time. So T to the power 0.5, so B is 0.5. If I increase the particle weight fraction, this reduces. So essentially this means that the film that was present between the two particles, the liquid film, starts to rupture, and the frictional interactions now will start to dominate instead of the viscous interactions. So this again becomes one of the reaffirming factors, since this kind of subnewtonian coalescence has been reported for polymeric solutions. In case of polymeric solutions, you have dissipation which is viscous in nature, but here the dissipation is frictional in nature. So this is the map that we had. So this was reported by Roish et al., where they have seen jamming at same critical fractions with respect to our study. So keeping in tune of this, we also decided to check that these rheology experiments, if we do it in the same configuration. So we have done an extensional rheology, so we are stretching the filament, and we find that at the critical volume fraction, this stretching leads to a filament thinning, which means there is an existence of jamming that we are trying to hypothesize. So I am going to skip the equations. If anybody is interested, please feel free to come and have a chat. So that's the major takeaway from the study. And these are some of the things that we are doing in our lab currently. So we have picked up another porous media, which are the sanitary hygiene materials used by women. And we are trying to study blood flow currently in these. So we have created, so these are made of banana fibers, and we are studying what happens or what kind of imbibition dynamics we see if we take water, plasma, and we have also separated the blood, like the components, the cell components from plasma. So there are two, I'm just going to play two of them just for, so these fibers are compressed and uncompressed, and you can clearly see that the wetting, spreading and imbibition changes. So most of them will follow the direction of the underlying fiber in case of cell components, whereas for plasma we find that it becomes asymmetric spreading. And we are also trying to create some of these hydrophobic barriers again over paper substrates, so that we can control the spreading and mimic what happens in real scenarios. So if you have heavy bleeding and light bleeding, the hematocrit value changes. How does it influence the velocity front in a lab scale? The other porous media that we are now interested in is the separators that are found in batteries. So how do electrolytes wet them, and what kind of solvents will be ideal for resizing your batteries or moving from lithium ion batteries to sodium ion batteries. So I think I would like to complete my talk over here. These are the students involved. Thank you, everyone.
Thank you. Question.
Hi, in the polymer capillary rise problem, you mentioned that the basic difference is that you get a T to the half regime crossing over to T to the 1/3.
Yes.
Is the T to the half attributable simply to enhance viscosity, or do you think something properly non-Newtonian is coming in?
So actually, what I didn't focus over here, because I was told that So elasticity is also a factor because the polymers we are using are not just viscous, they are viscoelastic. So they have a finite relaxation time. The problem is when we were probing it, the FPS we were probing it, those were beyond its relaxation time. So we couldn't separate the components. So yeah, I think
So
that
then
partially
for
answers.
that particular set of studies, it's really just the viscosity.
It's just the
rather than-
viscosity.
Okay.
So the
all right,
model
thanks.
also does not account for the elasticity.
I see. Okay. All right.
as of
Thanks.
now.
Thanks.
Any other questions?
So maybe I missed it, but I didn't see surface tension anywhere in any of these things.
I just did not mention it, but yeah, it's there. It's there in all of them actually. I'll just go if you go back. So the balance, if you see, the first one over there on the right is the driving force, capillary force. So, okay, I don't know why this is, yeah. So sigma over here is the surface tension. That's the one that's driving. It's being opposed by these three. And depending on the opposing forces, you have your different regimes. So if I talk of coalescence as well, it's capillary force that's driving. You have the van der Waals and electrostatic at the particle level that's opposing. But of course, we bring in frictional because it's a non-Brownian system. Had it been Brownian, then I could have just equated it with capillary forces. And as far as the second one is concerned, the polymeric solution, so this is the one that we are trying to do. But that's just scaling analysis. So we have not done the analytical modeling over here.
Sorry. There is something called a fountain effect with respect to superfluid helium-4. You keep it in a bucket, it just rises without rotation.
Yeah.
So the question is to you and Sriram, is there any...
He can probably answer, but I am superfluids. I have not really done much of a work.
Anything deep about rotation? It happens without rotation.
Yeah, this is a driven system. It's not the same thing.
And I'm wondering if there is any similarity or in... Okay.
We'll talk.
Thank you. I had a student doing a project on
last topic you left ion transport in porous media. So you wanted to say something which probably...
Oh, okay. So ion transport in porous media, we're basically looking at battery separators, like I said. So we're going to see how the solvents, so like dimethyl ether, DMC, carbonate solvents, and your electrolyte, which contains a salt, say a lithium salt, how it moves through these separators. So the time scale of wetting that we have observed is mainly because of the imbibition. So the amount that seeps through. But in industries, nobody really considers that. So they just fill in the electrolyte, keep it for days, and allow the separator to get wet by the electrolyte. So what we are trying to figure out is what kind of time scales those are. So we will resort to the classical electrokinetic models. So like take in the Stern model, Hellman's plane, and incorporate the tortuosity into that.
You commented like sodium and lithium ion battery.
Yes, so we are starting with lithium. Then we will move to sodium ion batteries. Yeah. But we can't do it without a glove box. So for now, it's till I figure this out, hopefully we'll have that.
Okay, then let's thank Dr. Goel. Any questions? For the interesting talk. Now we break for tea and rejoin at 11:20. And tea is served just outside.
My research group, we work in the field of biological inorganic chemistry, and since it's a very diverse audience that we have today, so I would like to, keep it the way so that it's understandable to large audience. So to start with, I will be talking about the redox active iron complexes, but before that, let's give a brief overview of what we do in the research group. So our research group, it's in the field of biological inorganic chemistry. We work with the biologically relevant ligands, and the ligands which are of our relevance are the one which coordinate to the transition metals in the redox intracellular environment. So this could not only affect the on-target efficacy, but also introduce new reactivity. For instance, redox chemistry of some of the transition metal complexes which are formed in situ. So once we make these ligands, their complexes, we utilize them for malignancy, cancer, and also at times for infectious diseases. Of late, we have started gaining lot of interest also towards neuro disorder, especially Lafora disease with the biological science department at IIT Kanpur. Now, as I said that, we start with the synthesis of ligand in our lab, we make their metal complexes. At times, we also do their nano aggregation or nano formulation. Once we have done that, we try to do the characterization in the in vitro setup, where we see what is the identity of the compound, what's the characterization in terms of what's the binding mode, what's the oxidation state, and all those properties of the metal complexes. Then we go for the in-cell study, where we establish their mechanistic profile, their biological profile, that if they are killing the cancer cell, what is specific cell death pathway they are following. And none of this would make sense if we do not show the translational aspect of our work. When I translational aspect, we mainly work with the animal models, especially so far we with the mice and rat models. And all of these experimental data are further validated by theoretical aspect. So of all the projects, as I said, we are working in our lab. I will be mainly talking about one of the major projects which has been recently published. So to start with, cancer, I will not go into the history of cancer. By now, I think most of us are already aware of different cancer treatments which are going on in around the world. And of all the cancer treatment, immunotherapy has made a major stride, to the extent that it's also said that in future, many surgeries will eventually be replaced by immunotherapy. So immunotherapy is playing a very significant role. Now what is immunotherapy? So when we talk about immunotherapy here, our own body's immune system, it is used to combat the cancer cell. Now when it comes to immunotherapy, it's not always, the results are not always very positive. So it varies among the patients even with the same cancer type. If I talk about mouth cancer, if I talk about colon cancer, even with the same cancer type, their feedback or their response or the efficacy of immunotherapy, it varies from patients to patients. And why is this so? Because of the immune characteristic of the tumor. Now, despite several transformative impact of immunotherapy over the period of time, very minute number of patients, they show positive response to the immunotherapy. And that's why this concept of the cold and the hot tumor was proposed, because it talks about the immune status of the tumor. So in order to predict what will be the tumor response, what will be the treatment results, it's very important to understand the difference between the cold and the hot tumor, what will be the intrinsic and extrinsic factors responsible, tumor microenvironment, and also tumor characteristics. So let's start with the cold and the hot tumors. So what are cold tumors? So these are the class of tumors which are poorly infiltrated with the immune cells, especially T cells. You must have heard about the terminology T cells in the immune cells. So in this case, it becomes very difficult for these, since there is hardly any T cells. So immune response is kind of inactive. At the same time, if we talk about the hot tumors, they refer to the they do show signs of inflammation. There is lot of infiltration of the T cells, and they are always ready to fight the cancer cells. Now, why these cold tumors, they evade the immune surveillance? What's the reason? And the reason is that they create a very immunosuppressive environment around themselves, and that's why they become resistant to the immune therapy, immune-based therapy. So that's why, you know, in the recent time, a lot of research is going on to convert these cold tumors into hot tumors, so that the tumor treatment, they are responsive to the immune-based therapies. So all the scientists, you know, many scientists, they are interested to understand if and how we can switch these cold tumors into the hot tumors. And the research obviously goes towards reversing the suppressive microenvironment which surrounds these cold tumors. Now, suppose even if I convert this cold tumor into hot tumors, how do I prove that? How do I verify that? So there are three major hallmarks which are present in the cells in general, which act as a marker for these immunogenic cell death induction. The very first one, I would say, is HMGB, which is one of the nuclear protein which is released from the nucleus to the cytosol, and it's also actually called as the danger or the alarm based protein. So these proteins, they alarm the immune system about the damaged cell. The second one is the ATP release, which is also called as the find me. So it's released outside the cell. This is the second marker for immunogenic cell death, and it helps to find the damaged cell. The last one is the Skell reticulin translocation. So these are certain proteins which are present on the surface of endoplasmic reticulum. So these are all different organelles which are present inside the cells, and together these three markers, they are known as the damage associated molecular patterns. So these are the three major markers. Other than that, you know, people who work in the field of molecular biology, they have found different markers other than these, but these are the three major markers. So if suppose today I convert the cold tumor into hot tumor, these are three markers which I will be looking for mainly. Now, despite all these advances, there are two significant challenges which is associated with the cancer therapy. The very first one, especially with the cold tumors, it's difficult for these drugs to reach some of these deeply seated tumors. And why is that so? Because there is very minimal vascularization, or if I say the blood supply or the blood flow, it's really low. So that's why these drugs, they cannot reach these deeply seated tissues or the cancer areas. Second one is the difficulty in the real-time monitoring of the treatment, particularly in the near IR range. So there is no non-invasive method to find how the treatment is going. Okay, if the drug is working, if the tumor is going down, if it's decreasing. So there is non-invasive way, there is lack of these non-invasive way. So that's when our role came in. We wanted to show the convergence of therapeutic and diagnostic. So we wanted to synthesize a class of compounds which can not only have a therapeutic potential against these cancer cells, at the same time they can help in the diagnosis or especially in the near IR region. So there is actually a very significance of when I am saying this near IR2 region, because if we go further down towards near IR regions, that's where we get a lot of background signals from other hemoglobin, myoglobin. So that's why it's preferred to have in the near IR2 region. So our research group, we have been working on histone deacetylases proteins and their modulators. What are histone deacetylase proteins? So based on the cofactor requirement, structure, subcellular localization, they can be divided into 4 different classes. So these are the proteins which are present inside the nucleus, and in short I would say they are important for the survival of cells because they participate in the DNA synthesis eventually. So these sirtuin proteins, if you see over here, these are the NAD+ dependent histone deacetylase present in the mammalian cells, and we are mainly interested in these sirtuin class of the proteins. So in our lab, we started making different analogs of these inhibitors or the modulators of sirtuin proteins. So we made approximately 80 different library of these sirtuin protein modulators in our, so we have a synthesis lab. And we started exploring these class of compounds by making, especially if you see this oxygen, nitrogen and oxygen binding moiety. So it shows that they have property to coordinate to the transition metals. So once we made these library of compound, we coordinated them with different transition metal complexes, and here is the one which is one of the most active compound which was found. So we coordinated with iron, Once we had these active compounds, we characterized them by different spectroscopic methods like crystal structure, EPR spectroscopy, Mossbauer, UV-Vis binding. It's very important before you move on to do any biological assay, the compounds that you are making in lab should be pure enough. And in case if there is an impurity, you will not know that the activity that you are actually getting, it's coming from the compounds that you have synthesized or any leftover or any decomposition product which is in there. So these spectroscopic characterizations are very important. So but before we moved on to do any biological assay, we wanted to characterize that what is the identity of these in the solution state, because we had the crystal structure, but we were not sure how is it existing in the solution. Now this is one of the media which is used to grow the cancer cell, especially most of the breast cancer cells, then colon cancer cells. So this is one of the media, and what was seen that our class of compounds, they are existing in the form of a nano aggregate. So if you see this DLS data, it shows that it is existing in the form of a nano aggregate. Now there is significance that why we want these compounds to be in the form of nano aggregate. So if you remember, one of the things that I mentioned, that it's very, one of the limitation of these class of compound is that their uptake is not that great. So these nano aggregate, it actually helps in the uptake more than the class of the compounds which were not forming these nano aggregates. Once we had the characterization of these compounds, we moved ahead to do this cytotoxicity and the cell-based cell death mechanism. So we did this study in 4 different cancer cell line, MCF7 which is breast cancer cell line, A549 which is lung cancer cell line, this is prostate cancer cell line, then this is more aggressive form of the cancer cell line, and this is healthy, just to make sure that our compounds, they are not acting as a poison. So you have to make sure that you also treat your compounds towards the healthy cells to see that they should not be toxic towards your healthy cell lines. So, and what was found that our FeL1 was found to be most active among all the other compounds that were synthesized. So here are some of them. Once we got the activity in the cancer cell line, we moved, so the story does not stop here. Once you synthesize the compound, once you screen them against different cancer cell line, that's when the actual story starts, because you don't know what mechanism of the cell death pathway. It's very much like this, if you are eating an antibiotic, eventually you have to know where is that antibiotic going, where is it targeting, what cell death pathway. So that's when the actual story starts. So we started with the cell death pathway study, and this study is done in the presence of different inhibitors. So we had inhibitors for the apoptosis, necroptosis, ferroptosis, paroptosis, autophagy. There are more cell death pathways, but these were the initial that we did. And what was found, that our class of compounds, it is undergoing autophagy mediated apoptotic cell death pathway. Now once we have proved in the presence of inhibitor, we wanted to further verify it by immunofluorescence assay, and what was used was LC3 puncta, which is one of the autophagy marker. So we saw these LC3 puncta coming on the surface of these autophagosome in the form of this green fluorescence which we see over here. So this is the immunofluorescence assay to further verify that that is the cell death pathway that they are undergoing. Now during this process of autophagy mediated cell death pathway, these class of compounds, they are iron complexes, so they are redox active. If they are redox active, they can go from iron 2 to iron 3, iron 3 to iron 2. In the process, they generate reactive oxygen species. So you must have heard about all these anti-aging drugs. Okay. So those are some of them, or most of them actually, they are quencher for these reactive oxygen species. So it means that all the time in our body, lot of ROS is being generated. And so this class of compounds also, it generates ROS, and that's one of the cell death pathway, you know, like it goes inside the cancer cell, participate in the ROS generation. This reactive oxygen species goes and targets different organelles, and one of them is it causes the glutathione depletion. At the same time, one of the protein which uses this glutathione. So glutathione is also one of the millimolar concentration antioxidant present naturally in our body. So the glutathione depletion is taking place. This is one of the substrate for the glutathione peroxidase protein, which prevents the lipid peroxidation inside the cells. So if this is getting depleted, glutathione peroxidase will get depleted and lipid peroxidation is happening. So, these are assays, I understand it's a lot of technical things over here, lot of dyes and all, but the overall concept what is we are seeing over here, that is participating in the ROS generation, and at the same time the other ingredients inside the cells, especially some of the antioxidants, then glutathione, they are being depleted or the lipid peroxidation is happening. In this cascade of events, it also causes ROS generation inside the mitochondria. Now, ROS or the reactive oxygen species, it can be of several types. It can be hydroxide, it can be peroxide, it can be superoxide. So, it is very important to understand what is the identity of the ROS that is being generated inside the cells. So, based on this MitoSOX experiment, we found that it is the superoxide radical which is being generated, and we saw the effect on the mitochondrial membrane potential also with these assays. Now, all these, as I said, events, the downstream events is that eventually we see endoplasmic reticulum stress is being. So, endoplasmic reticulum, it is one of the major site which leads to unfolded protein response cascade to get activated. So, what we started with? We started with where we want to convert the cold tumor into hot tumors. That was our initial goal, right? So, eventually that is what we want to do with these class of compounds. So, here this unfolded protein response cascade gets activated over here. There are two major proteins which plays very significant role to upregulate this cascade. One is the BIP protein and the other one is the PERK protein. So, both these proteins, they act as a chaperone for the misfolded protein to be converted into folded proteins. So, we saw that PERK protein, it is getting down regulated, whereas BIP protein, it is getting up regulated, which is one of the marker for the endoplasmic reticulum stress being activated. Now, coming back to ground zero, in order to show that whether you are converting the cold tumor into hot tumors, there were three major markers that you eventually want to see. The first one was this HMGB1 release, the second one is this ATP release, and the third one is this calreticulate. And we did see by immunofluorescence that all three of them does get affected. If you see this HMGB protein, it is going down, so immunofluorescence or the green fluorescence around these cancer cells, it is depleting over the period of time. The ATP, cellular ATP, it is being released, which is the find me cells, it is coming out, and the third one is the calreticulate protein, which is getting translocated from the endoplasmic reticulum to the cell surface, and we do see the increase in this green fluorescence over here. So, we started with class of the compounds, ligands, we made their transition metal complexes, we characterized them, and eventually through the cascade of different experiments, we eventually proved that our compounds, they are participating in the conversion of the cold tumors into hot tumors. But so far all the experiments that I have shown you, they were done in the 96 well plates, they were done in the 2D system, okay. But if you think about the actual tumors, they are in the form of 3D spheroids, right. So, we do 3D spheroids, especially like in those 96 well plates, but still they are not very translational, I would say. So, that is when we move to show them in the in vivo setup, where we do it in the biopsy mice. It is a 40 tumor one. So, here we inject or inoculate, so here we inoculate the tumor into the biopsy mice, and once the inoculation is done, once the tumor is established, then we do the intravenous injection for our compounds. After the intravenous injection, we do several dosage of 10 milligram from day 1 to day 7, and on the 8th day, and during this time period, we do follow up what is the tumor size, what is the tumor volume, how is the weight, if there is any side effect on the mice, if there is any something that should not be because many times you do the experiment in the in vitro setup. The moment you go from in vitro setup to the mice models, you will see that the effects are drastically different than what you are expecting. Same happens when you go from the mice model to actual patients. You are expecting that okay, everything is going fine, everything is working, but when you go to the patient samples, the things are quite not in your favor. So, we did see that these class of compounds, they are showing decrease in the tumor volume, and tumor weight was also decreasing, and during the process there was no side effects. We did not see any side effects on the blood cell morphology or the tissue morphology, and we also wanted to see what is the distribution in different organ. We did see some accumulation inside the heart, but one of the reason that we gave it, like we hypothesized about it, that most probably it's because of more concentration of mitochondria, that's why we are seeing more accumulation. Now, one interesting thing over here is that during the process, if you see, this is the control where our iron complex is not being treated, and this is the iron complex which we synthesized, so that is treated. And if you see the amount of the lymphocyte compared to the control, so lymphocytes were the cells which we want to be recruited if we want the immune induction to be there. Okay. So, these lymphocytes, their recruitment has happened, indicating that we have been successfully able to convert the cold to two limitations. One was high CD induction.
Your time is going to be up.
Yeah, okay, 1 minute. So, these class of compounds, they do participate in photoacoustic signals. So, this study was done with Dr. Sanhita Sinha Roy here in ISC Bangalore, and these class of compounds, they also participate in the near IR2 signal induction. So, where are we heading? Eventually, we want to have immortalized PDF cell lines and tumor organoids, so that there is a more personalized treatment. We can have organ on the chips, which can be, provided to people who want to screen their compounds. And with this, I would like to thank my past and the present group members, Indian Academy of Science for the associateship. I am also visiting professor at ENS, and thank you ACS and RSC for awards over the period of time, and last but not the least, funding agency for their generous grants and funding. Thank you, and I would be happy to take any questions.
Thank you, Dr. Vidya, for an excellent presentation. So I think, sum it up, what I understood is the glutathione thing. That's a very important molecule now, because people are taking it for anti-aging, and you really anti-age. If you look at Safali Janiwala's episode, it reduces your age to 42. So that's one thing, the molecules are very fantastic molecules, and it's an excellent piece of work. I enjoyed listening to you, and I open the talk for some questions, 1 or 2 questions, because
yes.
Yeah. You said cold tumor and hot tumor.
Yes.
Suppose somebody has a colon cancer, do half the people have cold tumor and half is it tumor dependent?
So, there are markers which are available. So, in case of, it's definitely tumor dependent, but as I said, in some cases immunotherapy does give very good response, in the other cases
No, my
not.
question is, suppose colon cancer, can you say it's a cold tumor?
No, you cannot.
So half. That's what
it will vary from patient to patient.
Okay,
we cannot.
That's what I want. Thank you.
Okay.
Please.
Just one question.
Yes.
You talked about the involvement of unfolded protein response.
Yes.
So you have looked at the POG branch. Have you looked at, do you have any idea whether the other branches like IRT alpha, 1 alpha, or APF6 has any role in this?
Yes. So, yes, you are correct that as I said, since we are not molecular biologists, so that's very diverse field of study that needs to be done, and people who are molecular biologists, they do study in lot more markers than what I have shown, even for the UPR cascade induction. So, no, we did not see, but that's something definitely over the period of time we will try to include in our study.
So, very nice presentation.
Thank you.
So, I want to ask one thing, because you showed that in the last, the CBC shows neutrophils and all those markers upregulated. But they may be upregulated because of the material you are giving. They are producing response against the material rather than your cold cancer cells is converting into hot cancer cell.
Absolutely.
So what is your comment on it?
Absolutely, you are absolutely correct that it might be because of inflammation, it might be because we are giving something external foreign, right? But what we wanted to show that, it's actually a combined effect that we are seeing along with the markers, along with recruitment of the lymphocytes, but what you are saying is absolutely possible. that it might be because of the compounds that we are getting, it's getting inflamed and the lymphocytes and all are increasing.
Ritika, you have shown a complex FeL1. So
Yes,
is
sir.
it soluble in water?
Yes, it is. But most of the time, one of the major limitation with our study is some compounds, they are not soluble. So
What
in
about
that
this
case, we try.
FeL1?
What is the FeL1?
No, you have shown.
Sorry.
You have shown.
Huh.
Yeah, you have shown in your slide
Yes.
that the complex which you synthesized, that you have indicated to be FeL1.
Yeah.
So it is having many aromatic rings. So these aromatic rings may render its non-soluble properties in water. So it is soluble or insoluble?
This one is soluble, but what happens in case if it is not soluble, we try to dissolve it in DMSO, but there is also condition with DMSO that there has to be this many, like 0.1% or less than 0.1%, so that it doesn't become toxic. So in that cases, we try to do different formulation to increase the solubility.
Last question.
Yeah, okay.
Hi, very nice presentation.
Thank you.
But most of your screening you are done in human cell lines. How you correlate with your in vivo, which is a syngenic model?
Yes. So what happened when we moved from our human cancer cell line to the in vivo model? So first we went for the immunocompromised Nordiskid mice, and there we tried injecting the same cancer cell line, the human cancer cell line. But first of all, they were very expensive. We are just into 4 or 5 years of our independent career. But eventually we are collaborating with the groups which can provide us immunocompromised mice, and we
because this MDM331, they are slow growing mice.
Yeah.
Better we can go with NSG mice so that you can get a better xenograph models.
Yes.
Okay. Let's thank Dr. Ritika with an applause.
Thank you.
We go on to the next talk is by Dr. Saran Athar from IIT Jodhpur, and he's going to talk about understanding hydroclimatic extremes under climate change and human influence, impact mechanisms and adaptation strategies. Dr. Saran.
Thank you, sir. So good noon everyone. I am Dr. Saran Athar, faculty in Department of Civil and Infrastructure Engineering at IIT Jodhpur. Oh, okay. Am I audible now? Yeah.
I think you should raise your mic a little bit.
Okay.
But the minute it's a bit up.
It's fine. Okay. Okay. So first of all, I would like to thank ISC for giving me this opportunity to present my work. So I work on hydroclimatic extremes, how these hydroclimatic extremes are changing under the anthropogenic climate, especially under the climate change and region-specific human activities. So before going ahead, we should know about the hydroclimatic extremes. What are these hydroclimatic extremes? So basically hydroclimatic extremes are hydrological extremes and climatic extremes, where we focus on hydrological extremes of flood, drought, or climatic extremes like extreme precipitation, heat wave, cold wave. So basically these extremes are deviated from the typical normal weather or climate. If you see here a normal distribution of any extreme, so basically we focus on the lower tail and the higher tail of the data set. So if that is in the lower tail, basically we focuses on the cold wave or droughts. If it is on the higher tail, we are focusing on the heat waves or floods. So and basically these extremes have very low probability. So when we design an infrastructure or when we do some assessment on some sectors, maybe agriculture or energy or ecology or maybe the human health, that time we focuses on these low chances of the extremes. Those can occur over region. So climatic extreme, today we will focus on the extreme precipitation, flood, heat wave and drought, and these extremes pose significant impact on water management or water resources, food or agriculture, over energy infrastructure and renewable energy generation, over ecosystem, forest fires, human migration and the human health. So before we discuss about the impact of climate change and human activities on hydroclimatic extremes, first of all we should know why these hydroclimatic extremes occur. It is not like these extremes occurring recent days. Those are occurring like hundreds years ago, like the starting of the earth. So during the starting of the earth, or maybe without human intervention, these hydroclimatic extremes normally have some specific cycle. So if you see, this is the temperature cycle of earth in the past thousands of years ago. So here you can see there is a natural variability in the temperature as well as in the CO2 emission. But in the last few years, we have seen the significant increase in the temperature and the emission of the CO2 emission, and that pose significant impact on the characteristics of the hydroclimatic extremes. But during the without human influence, why there is this natural variability in the occurrence of the hydroclimatic extremes or the temperature? That is basically due to the natural variability, the variation of the orbital distance between the earth and sun, and the volcanic eruption and solar cycle on the earth. And due to that, these phenomena, natural variability, there is also one major driver of these hydroclimatic extreme, that is El Nino southern oscillation, that is basically the warmer temperature condition in the Pacific Ocean. And due to this warming Pacific condition, it affects the wind condition and the monsoon over the different parts of the globe. So when we have the warmer condition in the Pacific Ocean, the Indian subcontinent receive very less rainfall, and that affect our Indian summer monsoon. And these INSO effect have like the occurrence of like 2 to 7 years, and it has 3 phases: warm phase, cool phase and the neutral phase. So when it is in the warm phase, there is a deficit in precipitation over Indian subcontinent. When it is in cool phase, then there is a surplus rainfall in our Indian subcontinent, or we receive more floods or extreme precipitation. If there is a warming condition, then there is a drought or heat wave over the Indian subcontinent. But due to the human intervention or human activities over Earth's global temperature, or due to the global warming, the temperature has increased in past 100 years, and due to that there is a changes in our hydrological cycle. There is an increase in the atmospheric water demand that now can hold more amount of moisture or water in our atmosphere. Due to that, they can cause more amount or extreme amount of precipitation, or maybe the severe amount of droughts or flood. So that we have also like experienced in the recent past. In every year we receive flood or drought, and many studies has reported that these type of hydroclimatic extremes has significantly increased in the past 10 years compared to the reference level of 1982-2010. And due to that, there is a significant impact on our socio-economic condition. So that's why we need to understand these hydroclimatic extremes, how these hydroclimatic extremes will affect different sectors, how they impact the water resources, energy sector, socio-economic condition over agriculture and other sectors, as well as how the mechanisms those cause these hydroclimatic extremes are changing under the climate change and the human activities. And as this global warming increasing, there are different scenarios, and under these scenarios, how these extremes will occur in the future. So, at IIT Jodhpur in Hydro Monitoring Lab, we are focusing on the three major aspects of the hydroclimatic extremes, and we would like to address this major scientific question that how we can develop effective adaptation strategies to reduce the risk of hydroclimatic extremes on infrastructure and other sectors. So, we focuses on the impact of hydroclimatic extremes, how these hydroclimatic extremes are changing under the climate change and human activities, and how the risk of these hydroclimatic extremes are increasing on the infrastructure damage. Then we are also focusing on the processes, mechanisms and the drivers of the hydroclimatic extremes, and at the end to develop the effective resilient strategy or adaptation strategy, we should know the when these hydroclimatic extremes occur and what are the conditions in the real time. So, we also need to do the monitoring of these hydroclimatic extremes. And these all three verticals are connected to each other. If we want to do the reliable monitoring of the hydroclimatic extreme, we should know what are the processes behind these hydroclimatic extremes other than the known processes. There are many processes, those are changing due to the climate change and the human activities. At the same time, we also need to understand how the risk of these hydroclimatic extremes will change as the processes are changing, and it will also affect our monitoring system or modeling techniques. So, first we will discuss about the impact of climate change on hydroclimatic extremes. So, due to the climate change, there is a severe occurrence of the heat wave over the Indian subcontinent. So, recently in 2022-2023, we observed a mega heat waves, and these type of mega heat waves will occur very frequently in the future warming climate, and after 2040 these extremes are very frequent. Similarly, the drought frequency and the severity will also increase significantly over the Indian subcontinent, especially in the northern and the northwestern region of the Indian subcontinent. And due to these heat wave and droughts, there is also the risk of compound risk of heat wave and droughts. So, previously there is less risk of heat wave and droughts occurring together, but due to the climate change, now these extremes can occur together with more severe impact on the agriculture or water resources sectors. Similarly, the extreme precipitation, since due to the climate change moisture holding capacity has increased in our atmosphere. So, extreme precipitation and floods will also increase in the future climate, especially in the central part of the India. And other than this, since we have number of global climate models, those project these climate change, and the uncertainty in these climate change are very high. So, we need to provide the reliable information of these hydroclimatic extremes. If we use some bunch of the models, they may provide other kind of risk or other values of risk. If we use different set of the global climate models, they will provide different set of risk indicators. So, we need to do the uncertainty analysis, and we need to provide the reliable information of the future climate, so we can design our future infrastructures accordingly. So, other than that, these hydroclimatic extremes pose severe in our dam infrastructure. In India, we have more than 6,000 dams, and these dams are severely affected by the extreme precipitation and the floods. So, in the recent years, the risk of extreme precipitation has increased, and that will pose severe impact on these dam infrastructures. Similarly, the energy infrastructure is also under threat under the heat waves, and in the Rajasthan we can see where we have very less density of energy infrastructure, the disturbances of the energy infrastructure is more, as well as Rajasthan is famous for the renewable energy of the solar and wind, and due to the climate change there is a significantly decrease in the wind renewable energy over the Rajasthan. So these are the few changes. These are the few impacts on the hydroclimatic extremes and different sectors of the climate change. Similarly, there is changes in the mechanism, processes, and the drivers of the hydroclimatic extreme. So one of the driver we discussed, like the INSO, there are number of drivers, Indian Ocean Dipole and the other drivers, oceanic drivers or atmospheric drivers, those affect these hydroclimatic extremes, and due to the climate change these drivers are the processes and the impact of these drivers are changing with the climate change and the human activities. So normally we use hydrological model or land surface model to assist how these processes, drivers or mechanisms will change due to the human activities and the climate change. So for example, we use this variable infiltration capacity model. Using that we can assess various unknown hydrological components, those are not available and we can identify what kind of processes are dominating in a particular watershed, and those can change due to the human activities and the climate change. Similarly, is the impact of air pollution concentration on hydroclimatic extremes and how they will change at different regions. So for examples, the drivers of the mega heat waves, those will change in the future warming climate. We are receiving more amount of mega heat waves even under the neutral condition of the El Nino conditions. Similarly, the industrial aerosols are also increasing the risk of droughts in the future warming climate. Other than the droughts, there are flood mechanisms are also changing. There are different flood mechanisms, maybe meteorological conditions or watershed based characteristics based mechanisms. Those are also changing specifically due to the human activities, regional based human activities like the dam operation, irrigation, groundwater abstraction, or the unplanned urbanization. So those hydroclimatic extremes are also changing under the different human activities. So to deal with these increased risk of hydroclimatic extreme, we require reliable information of the hydroclimatic extremes. So we developed this India drought monitoring system using the land surface model, where we have not considered human influence till now, but in the future, right now we are including the future influence zone. Similarly, we are developing this hyperlocal heat wave early warning system that can provide the heat wave early warning information, as well as we can reduce the impact of urban heat wave or urban heat island impact on our cities. And there are substantial human activities at a local level. So now we are including those human activities in our modeling techniques and to understand how these hydroclimatic extremes will change in the future. And due to the effort of the scientific community and the effort from the government side, there is a decrease in the climate mortalities in the past 100 years. So previously in the 1920s, those are very high. Now due to the development or the scientific advancement, those numbers are very less. And we have developed few data sets, those can be used by different researchers and students. Those are available at our website. Thank you.
Thank you, Dr. Saran, for a very interesting talk.
Thank you.
Apparently, the future is looking not so very bright. I think all of us have to be aware of that, I guess. Especially we burn so much of coal. 60% of our electricity is made from coal, and we are going coal. That's what I understand, actually. So apart from that, I think it is a very interesting study. So the talk is open for some questions if you have. Yes.
You said this hydroclimatic extremes in the past has happened because of volcanic activities.
Yes, sir.
Can you take
not
that as a
only
measure?
the volcanic activities, sir. Not only the volcanic.
One of them,
yeah.
solar cycles and so
yeah.
on. So can you quantify whatever human beings are doing to the earth in terms of volcanic activity units? Like it's equivalent to 10 volcanic activity, whatever you have done.
Okay, so
maybe a good idea.
That is very interesting question, sir. I have not done this kind of study, like how the human activities equivalent to the one volcanic activities. Yeah, but it is interesting to find out. That surely I will do.
Any other questions? Yes.
So we have two kind of human activities. Indirect human activities, those cause climate change, and there are few regional based direct human activities like the dam operation or irrigation or changes in the local water cycle. So both can influence the hydroclimatic extremes.
There is one from the fourth row. Somebody raised the third row.
I didn't get anything about what you have done in this presentation. Your own contribution has not been highlighted.
So sir, we do study of so.
I know, but this is a very general, talk. There's no mention of your work.
So sir, when we do the analysis of these hydroclimatic extremes, these 3 points are very critical. The impact, how the climate change will impact the hydroclimatic extremes. So first we have analyzed how the risk of hydroclimatic extremes will change due to the climate change in the future. And we have provided very reliable projection of these hydroclimatic extremes that I have mentioned in few of my slides, that how these few models can, if we select a few models, how they can project a different kind of scenarios of hydroclimatic extremes. That is one vertical of the impact of hydroclimatic extremes. Another vertical is the processes behind hydroclimatic extremes. So we have also analyzed like how the extreme precipitation may affect the floods occurrence. It is not always possible that all kind of extreme precipitation will cause the flood. In few regions, there are like one day extreme precipitation can cause the flood. There may be few regions where multi-day extreme precipitation cause the flood, and in the few regions there are few dominating areas, those can cause the floods. However, I have not discussed all the points in detail due to the time limit.
Okay.
Yeah.
Okay, so I think that's a good message that you have to blow your own bugle a little bit more. So I think with that we close this talk and go on to next talk by Dr. Poonam Chandra. She is from National Radio Astronomy Observatory, and she's going to talk about exotic stars and their explosive demise, connecting the dots. Dr. Poonam Chandra, please.
afternoon, everyone. It is really my pleasure to be here, and thank you, IASC, for having me here. Dr. Sharan talked about. Is it better? This is, I think. Hello. I think I'll get louder with time. All right, so Dr. Sharan talked about Earth and environments, and I'm going to take you beyond the Earth, not just beyond the Earth, beyond our Milky Way, in other galaxies. So we'll be talking about exotic stars and their explosions, and I'll start with the fact that why is it not working? Okay, this is not working. Oops. All right. Okay. Wait, how? Sorry. This is working? Okay, let's try again. So our comprehensible universe has around 200 billion galaxies. Each galaxy has around 100 billion stars, and stars are being formed in these dark nebulae. And stars are being formed in the quantities of hundreds to thousands. And the beauty of that is, if you study them, you know that they were all formed at the same age. So if you have different kind of stars, you can study their evolution, and it has been seen that if you take stars in a star cluster and try to rearrange them in terms of temperature increasing from right to left and luminosity or intensity increasing upward, they don't occupy random spaces. They are in a very well-defined structure, and different kind of stars occupy different well-defined place in this luminosity temperature diagram, and this is probably the most famous and most useful diagram in stellar evolution, and it is called Hertzsprung-Russell diagram or HR diagram. In this diagram, our little sun is somewhere there, and we all know that sun is giving us energy by hydrogen fusion into helium, and once that happens, and there will be not enough density and pressure, and the sun will stop any kind of fusion in another 4 billion years or so, and it loses outermost envelopes and become a white dwarf, which will occupy that place in the HR diagram. So that's the fate of our sun, but we are not talking about sun at all. We are talking about the stars, which are very, very massive stars, and they have very high temperature, very high luminosity, and they get enough density and pressure that they not only burn hydrogen, but they also burn much advanced nuclear fusion. They do advanced nuclear fusion and burn heavier elements until the iron core. In this evolutionary stage, they become supergiant, and one of these we know is Betelgeuse in our own galaxy. And if you look at the size of Betelgeuse, it is the size is orbit of Jupiter. So that's big they become. But the more interesting aspect is that these stars, they will all end their lives in very explosive demise, and that's called a supernova. And this is a topic which is close to my heart, so I study these. And in these supernova explosions, of course, due to the own gravitation collapse, the star will collapse, and you know, this is probably the most extreme physics studying laboratories in our universe, because you cannot create these on our Earth. The energy which is coming out of this supernovae is 10 to the power 29 or 29 orders of magnitude higher than atomic bomb which happened on Earth, or which we can produce on Earth. And these are electrons are reaching extremes of energies, and to tell you this fact that every second in our universe around 8 to 10 supernova explosions are happening and giving rise to this kind of energy. So this is a very extreme fact, and that's why we love to study supernovae. But since I have to connect everything to the Earth, I have to tell you that supernovae are the only and the only sites where these heavier elements are formed. If there were no supernovae, we wouldn't have any oxygen to breathe right now, so we wouldn't be sitting here. So that means when the supernova explosion happens, all these heavier elements which were synthesized inside the star do explode and they come out in the environment. So we do know that before our solar system was formed, there must have been supernovae explosions, and that's why we survive. So anyway, so this is another implication for studying these supernovae. But now the question comes that there is a massive star. We understand that this will explode as a supernova. But how do we complete this gap? How do we understand? We already know that there are so many different kinds of supernovae, so we know that they are following different evolutionary paths, but we have to understand what path. And that is what we are trying to do in our group, and we are trying to understand what kind of different conditions are there which will give rise to different kind of explosions and what those explosions will look like. So from the massive star evolution perspective, there are some of the things which can affect the evolution is nucleosynthesis, magnetism and binarity, and in our group we are currently mostly focusing on magnetism and binarity. And in magnetism, I have to just say a little bit about magnetism. So these are these three different kinds of stars, and what we know is that these less solar mass, less heavier stars do have this convective outermost layer. So electrons are moving, so there is convection going on, and hence it's easy to have magnetic field. That's why stars like our sun do have magnetic field. But these much more massive stars, they are radiative. They should not have magnetic field. But contrary to our expectation, we see in our Milky Way that at least 10% of massive stars have these kilogauss bipolar magnetic fields. We do not understand their origin. We are trying hard to understand, but we do not know. But we do know that they do explain, or they can explain some of the exotic phenomena in our universe, including some of the LIGO black holes and exotic explosions. And what is a better way to understand magnetism than radio emission? And this is what our group is trying to do. We are trying to understand the radio emission from these magnetic stars in terms of gyrosynchrotron and electron emission. And currently, we are focusing more on electron cyclotron maser emission, which is 100% circularly polarized, and that comes because of anisotropy in the electron distribution from the magnetic null of the star. So that's a star and the magnetosphere. And we expect these kind of, okay, it's not working, but we expect these kind of emission circularly polarized from here. And inspired by this, we did a survey with the GMRT, the Indian Radio Telescope, Giant Meter Wave Radio Telescope, to understand this electron cyclotron maser emission. And this is one of the example of what kind of data we were getting. This was Bernali Das's thesis, and she finished in 2021. And in her survey of 35 stars, she ended up discovering 14 stars, and I have to say that there are currently only 18 stars which are known to have electron cyclotron maser emission, and 14 have been discovered by Bernali with our Indian telescope GMRT. Significant that Bernali received the TIFR's Best Physics Thesis Award, as well as Astronomical Society of India's Best Astronomy Thesis Award. So her work has been really influential, and it is, I would say every time a moment of pride when your student surpasses you. So I'm very, very proud of her work. So she has done really great work. And we have not just stick to this, we are trying to do physics with this. We are trying to understand the magnetic topologies of these stars, trying to understand the environments, because electron cyclotron maser emission is a very sensitive function of the densities. We are also trying to understand the binary system with magnetic fields, and with the data from GMRT and MEERKAT, which is a radio telescope in South Africa, we have tried to, we have seen that wherever there are these magnetic reconnections in these magnetic line fields, we do see this radio emission. This is a coherent radio emission again. This is ongoing work, and we do not understand where the radio emission is coming from, but this is this formed Ayan Vishwas's PhD thesis when I was still at NCRA until 2.5 years ago. Currently, I am at NRO and I am running this Chasers group, and I have this set of excellent students who are doing this amazing work. And in this work, we are trying to approach from the post-explosion perspective and trying to understand which star is going to become which kind of supernova. And the technique we are using is this novel, I call it time machine technique. It's called circumstellar interaction. So the idea is that stars are losing mass because their outermost layers are less gravitationally bound. And in our Milky Way studies, we have seen that the mass loss rate from the stars are pretty amazing, and they are dependent upon the escape velocity. So this means these winds which are lost from the stars are moving with around 10 kilometers per second or 100 kilometers per second. Now when the star explodes, the explosion ejecta moves with tens of thousands of kilometers per second. Now imagine it's going into this wind which was lost before the star exploded, and it is moving with 1,000 kilometers per second. It's simply like, you know, you don't like my talk, you start running, but I come behind you with a scooter, I catch up much faster. Which means if I do an observation one day after the explosion, I am catching how the star was losing mass 1,000 days before explosion. If I am studying 1 year after the explosion, I am catching 1,000 years before the explosion. And this is why I am calling it time machine, and this is the study we are doing right now. And what happens when this ejecta hits the medium, it creates these shock waves, and in these shock waves temperature become very high and it creates X-ray emission, and also it can emits radio emission and multiple emission in multiple bands. So for the radio studies, we are using GMRT, we are using Australian telescope, we are using Atacama Large Millimeter Array in Chile, and we are using the VLA in USA. And the radio emission is coming from the shock because electrons are accelerated. Just to give you a ballpark number, electron which has around 511 kilo electron volt energy, it has to reach to GeV energy to produce synchrotron emission at 1 gigahertz. So it means electrons are really reaching relativistic energies and producing synchrotron emission, and since radio is the lowest frequency, we see it for a very long time. And the thing is, the beauty is that in Milky Way, we know that different stars at different evolutionary stages, we know how they evolve. So this is when we study these supernovae, this is a compilation of several supernovae. When we study their light curves, by studying their light curves and modeling, we can predict what kind of star is giving rise to what kind of supernova. And that's really amazing. We have focused on low frequency emission. This was Nayana's thesis. Nayana is, she was my student at NCRA, but right now she's a postdoc at Berkeley, and she's doing amazingly well. She focused on this low frequency part of the radio studies, because this is where different kind of absorptions are happening, which is giving rise to different kind of physics, such as environments, mass loss rate, magnetic field, the shock velocities, and so on and so forth. And she did really amazing work, and this work is being, we are taking it forward. And currently with GMRT, we are running this GLIMPSE program, GMRT low frequency investigation of progenitors of supernova, and it has been very successful program. And for X-ray studies, we are using all these space-based telescopes because X-rays cannot reach Earth. So all these, most of these telescopes are NASA telescopes, except XMM Newton, which is European telescope. And X-ray emission comes because the plasma is super duper hot, and that's why. But it does give a lot of information depending upon whether the plasma is adiabatic or radiative. So this is just one example, and this is a little bit old study, but I wanted to give you example because this tells you that how one can derive science. And the thing is that this kind of study is extremely difficult because space-based telescopes are extremely difficult to get time. This was probably my only proposal, or maybe only supernova so far, where we got 6 epochs of Chandra X-ray telescope time. But the beauty is that you can see within like few days and few years, the spectrum is so different. And this spectrum gives information about the line of sight column densities. It means it is telling you the atmosphere. And if you look at the days since explosion, it's 1,000 days. And just multiply it by 1,000, and that's what we are probing, the progenitor history and how the environment is changing of these progenitors. More recently, we have done the study of a very close by supernovae. This is again Chandra. By the way, this Chandra is not my name. This is the name of the telescope. Please remember that. So this is the Chandra X-ray telescope spectra, and again, by studying the X-ray and combining with the radio data, which we took with VLA, GMRT, and many other telescopes, and combining with the optical telescope, we are able to recreate this whole progenitor evolution history for a very, very long time. So this is kind of science we are able to do, and my current student Raphael is able to, he is focusing on multi-wavelength studies of supernovae, and this is one example where he has used optical, infrared, radio, X-ray data to understand. And what we are understanding is that the explosion which is happening is not happening in a spherically symmetric medium. With more data, we don't have to model a spherical cow. We can start to model a realistic cow, and that's what we are starting to do in our group. ELISA is focusing on much, much later epochs where hardly any data exists. As you can see, this is only one supernova which has been observed for that long, and from these studies we are able to see that in some particular supernovae the mass loss starts much heavier mass loss starts even in the helium burning stages and those kind of things. So it's really impressive work. She's just going to submit her paper very, very soon. The other thing which we are focusing, this was actually, so this was our work in 2023. We were working with ALMA millimeter telescope in Chile, and we were expecting to see the dimming flux, but we actually saw the rebrightening, which was very surprising. And then Anika is working on this to understand that how you get, instead of dimming, you get the rebrightening. And how we understand is that a star was, when it was exploding, it had a binary companion which was creating this shell of mass loss which stayed far away, and when the shock moved in this direction, the shock, this is where when the shock moved, it is where the rebrightening happened. So this is really, you know, and that was early work in 2023 when we did. Now Anika is extending those studies with Chandra telescope and VLA and GMRT telescope, and we are trying to make a coherent picture with this. So I would just say that when we started this work, we have been able to see the many, many rich histories of progenitor evolution, asymmetric environments, multiple shocks, enhanced mass loss state, inhomogeneities. We are able to do science of energy budgets of how much energy is going in electrons and magnetic field, and this work is still going on and it's really exciting. But I did want to say one thing, since I have 1 minute and 29 seconds. I wanted to say that the richness of universe doesn't end here. Every supernova, which is gravitation collapse supernova, makes a neutron star. And when these neutron stars merge, that's when the watershed events of the centuries happen. And that's what happened in 2017 when two neutron stars merged. They created gravitational wave as well as electromagnetic wave. And for the first time and the only time, we saw emission from all the frequencies, and we saw it in gravitational wave, we saw it with gamma rays, X-rays, optical and everything. And in fact, the work which came out had 4,000 co-authors. It's probably I'm one of those, you can't see me, but this is probably the largest collaboration on this planet universe, and it did tell us a lot about cosmology, and you know, it tells us gravitational waves exist and they move with the speed of light. And I would end my talk is that this is the.
You had highlighted your name well.
Oh, sorry. I don't know how is it not. No, the names were at the back side, you know. There were just so many co-authors, independent collaboration. I know that high energy physics people are used to having the large collaboration, but this was exotic phenomena. Anyway, so I wanted to say that this is what we are trying to understand, explosions, second explosions, and studying them. And this simple picture of supernovae classification, our work we have converted into a much more comprehensive picture, and this we have just submitted this work, and we are now defining supernova instead of optical spectrum but based on interaction in radio and X-ray band. Thank you so much.
Thank you, Dr. Poonam Chandra, for a very fascinating as well as very frightening scenario about our universe.
Thank you.
It's really frightening to say that, when a star explodes, the explosive strength is somewhere around several orders of magnitude of an atomic bomb. I didn't know that. I know. Particularly about the sun, I was listening to that. It's not going to go away in 100 years. So we are not going to be there. So
that fraction of a second is enough to destroy us, by the way.
I just wanted to make one more remark before I, leave this talk for questions. You said about Chandra's telescope. I told you about Dr. Chandrasekhar's
yes,
name.
Yes.
So and your last name is Chandra, but I guess National Radio Astronomy Observatory will soon have a Poonam telescope. Not to confuse with Chandra, not Chandra 2, but Poonam. I congratulate you for an excellent talk, and now it's open for discussion.
Thank you. Yes, please.
Yeah. Krishna Kumar.
Yeah. I have a rather simple question. So you said the heavier stars, much larger than Sun, some of them have a dipole magnetic field. So what is the reason for this?
Yeah.
And also the second question is, all the stars don't have this dipole magnetic field, or the larger one. So is it a part of the life cycle of the stars?
Yeah, so I would say that there has been a lot of studies on this, and this is still an open question. So there are two, after surviving theories, tons of theories, two have survived. One is the fossil field, means the nebula which is forming the star itself has a slightly higher magnetic field than other nebulae, and when this is condensing, it is creating. But the problem with that model is that not all stars show this kind of magnetic field. We have studied the stars in binary, and we see that one star has magnetic field, the other doesn't have magnetic field. So that doesn't fit with the fossil theory. The other is people are saying mergers of stars. If two stars merge, the differential rotation of the star can create this stable dipolar magnetic field. There is no proof of that, but that's true for astronomy. You get just bunch of photons and you have just handful of physics laws, and you try to derive all these big things in the universe, but that's how the physics work. But what simulations have that you can actually create these stable dipolar magnetic fields by merger of stars. But this is again work still under simulation, and we still are studying those kind of things and seeing if some observational clues come for that.
Maybe we can take one more question. Yeah.
Any impact on Earth's climate? Because as a geologist, we learned that past supernova impacted Earth's climate, where the Earth's climate warmed and
we are nowhere close to Earth. We are nowhere close to Milky Way. The last supernova in Milky Way happened in 400 years ago. And so we are in far away galaxies. It doesn't affect. We had done some studies, and if a supernova is 30 parsecs away, then it may affect little bit. But in 2004, there was an explosion had happened in a soft gamma ray repeater, which had, if you were listening to radios at that time, it did affect the ionosphere of Earth. But that's the closest we have gotten so far. So we are safe.
I think we shall thank Dr. Poonam for an excellent presentation.
Thanks.
The last lecture in this session is by Dr. Kirti Ramatirtham, and he is going to talk about a smart way to solve problems. I'm looking forward to it actually, because I never knew there is a smart way to solve problems. So he is going to teach us how to do that. Dr. Kirti Ramatirtham, please.
Okay. So thank you for coming to this last talk of the morning. How did you go forward? The previous talk you heard is a good gives a good go forward to this talk, because she talked about the rest of the world, the rest of the universe. I'm going to talk about this Earth, that we had to work on problems which are of daily requirement, and satisfying the needs of people in a certain limited way, like low cost, low error kind of thing. So this is the opposite of what you heard. We could someday put together the two of them in the same slide. So the talk is about smart systems. How many of you know about smart systems? Have heard of smart systems? How many of you are carrying one? Exercise also. So, anyway, smart systems, you'll hear the technical meaning of this when I go forward. I'm from IIT Bombay, actually, but I'm currently in SAI, helping them to establish a department of data and science, data and all the other sciences. But fortunately, there are only so many now, not in millions, but in sense of numbers, in numbers. So I'm going to talk about the way in which we can solve problems, or address the questions that people have in the context of energy management, but this is a more general purpose use, as you'll see. So what is smart? Smart involves producing enough answers and in sufficient accuracy that it will be useful. Okay, the world is changing continuously, as you just heard, and how do you, in spite of the world changing continuously, how do you sense meaningfully? How do you sense? How do you analyze? And how do you respond? That's what we do, right? We hear people talking. We try to see how two such conversations can be put together to get something of larger magnitude, larger accuracy, and so on. Yeah. So the point is, if you hear everything around you, try to put that together, that will be meaningless. So there will be in different domains, different approaches to handling the data, and so on. So how do you decide what is meaningful? That's one of the questions. We normally decide based on our background, what is part of the psyche, the brain, and so that is how we learned how to do meaningfully. But there's more than that. There's something you can specify and be strict about it. And analysis, all kinds of analysis tools are there. The result of the analysis goes into this third box, where some more processing is done to determine who is going to be looking for the data. You respond to that, and also you hypothesize that you will have more people, more locations at which this data will be useful. So you want to remember that and go on and publish the data to that group. So that's the basic idea behind sense meaningfully, analyze and respond and remember to do it. Now, why does remember? Remember is there because we all do this, what's called reinforcement learning. You all know about this because the Nobel Prize was won by people who worked on this topic. So how do you know who requires it, and how do you know how to send it to them? So part of the mechanics of executing this sequence, and that timeliness is also important. See, if you read some paper today, there's an article in it. If you just tell somebody a month later, they won't have any interest in it. You want to give the answer, pass on the answer in a fixed amount of time, and that too. We may have different deadlines for different kinds of importance levels. We want to adjust that according to what's available in terms of resources. Are you with me? So we have sense meaningfully, analyze and respond and remember as the third element of the cycle. This keeps on going. As we go along, as we walk along, You gather more data, throw away some of that, keep the remaining. That affects your subsequent dealings with the machine, and then you go decide what to do with it and respond accordingly. Okay? So that is in a timely way. Now with this in hand, you can do other things. Then you add them together. For example, if I'm doing a smart principle applied to energy management, I see that there are three important questions to ask. How do you use energy carefully, and in particular necessary consumption of that increases the cost of what you are consuming. So we'll use a technique called opportunism. That's why we get the whole problem with carbon-based power, because we have the carbon footprint to worry about. So what we'll do is we'll flatten the peaks. Normally, if you see a picture of this, if you see a picture of the consumption profile, it will be exponentially down quickly, increasing, going down quickly, and so on. So what will happen is that when we have energy which is being used by a large population, and it is not of a constant type, then we have to worry about the peaks that will appear and use techniques called that I'm denoting by exploit renewables. Now, and so you do that by storing excess energy during the off periods, nights. Nobody's using it because from the other types like which are the type where you can store it. If you don't need it, then that is stored energy is not going to be used. But the things to be used. Oh, okay. Let's have this. So I'm going to take you through three examples. So if you have a need for any technique which is based on this, let me know. They can learn from one cycle to the next. They can learn from the neighbors, and you can also monitor the system yourself to figure out how things are moving. So here we have a smart classroom where we have applied many of these techniques. You'll see that in a second. There are about 10 examples we can give you, which have been implemented and all that. But I'll focus on 3 or 3.5, and depending on time. So the first, this example, what we are aiming for is to make sure that there's energy consumption only if there's occupation in a space. Right? For example, if you go to an auditorium in a university, you'll always find that it's on. Because it's the easiest thing to do. And it's also true of classrooms and some faculty offices. So but you don't have that being satisfied. What will happen is that you will have energy being used, but nobody is sitting in those spaces, or no need for that consumption going on at the time. So how should we worry about this? We should first thing I want you to do is to create a state machine that that takes you. This is very temperamental. Oh, going wrong direction. Okay, fine. So we have a state machine which tells us what states you go through and what triggers the state transition. So you have here, we can't probably read it. I'll take you through this. We're moving already. Okay, so first is you have cameras in the room, and they tell you what you're looking at. So this first thing says head found, head not found, as the case may be. Then others are lights, fans, those are marked in the circles. And the edges represent the transitions. For example, when you're in a head not found situation, this is this curve. Yeah. Oh, okay. Keep it empty. That one, first one. This is not me. Okay. You can see that you're going from a state which is, says HD, HND going to go HD to the HD's state, right? So that means that when you're in an empty state, nobody is there, then the head appears, detected by the sensors, then you're going to get to the state where it is occupied. Okay, with me? So, then from there you have stuffiness, hotness, chillness, all of those possibilities. Depending on what really happens, it moves to one of the other states. Bottom line is, if you look at this movie clip,
Yeah, there's going to be a movie. Yeah,
stay for it.
Yeah.
Okay.
Okay. Let's move on to the next one.
I'll take it. Okay, so now you got the idea that things move as state changes, and it's up to you to go to correct state so that the semantics of the application you're in for, that is satisfied, the cost is low. Okay, low by design. And here we have a situation where we all know about the way rooms are scheduled in our offices. The classrooms are always on, the AC is on, lights are on, and people come in and go. Nobody takes responsibility for the adjustment of the AC's switches or anything like that. Because of that, there's a lot of energy wastage. I'll show you some examples. Okay. So the examples illustrate to you that very simply you can understand what the state is, and how you go from one to the other depends on the state that prevails with regard to the space in the room. For example, let's look at this example, this auditorium. Go for it. That's okay.
So this is the. You want me to take over?
I'll take it. Okay, here. These boxes represent a particular slot and which class is being held there. Okay, for example, you see CS 743 to 31. 743 is going to be held there in room 201, and if we have more than 53 people, they can't be managed. They have to reorganize it. But that's the assumption people use because the office has given them the requirement. Okay. What we do here is to show that if you have a class schedule which is based on all these inputs from the various sources, you will come to a situation where there might be some mistake in the assignment of the rooms, or you're going to have rooms attached to people. What do you do in this case? You automatically say, let's close the AC for 1 hour. But we know better, right? Because we know in the nights when we go to sleep, we keep the fans at a certain value for the set point, which will allow you to move forward without paying the price for the 1 hour of spent fuel on AC, right? So now can we do this more methodically? Methodically, that's what we show here. The scheduling is based on pre-cooling, where we use the fact that it's been around, and the room is not being used now, but that doesn't mean it's not going to get used. So the requirement I had there, which said that it should use, if I can remind you. Okay. So energy consumed only if occupied will be satisfied only in cases where there's no other hope to use that the cool situation, which is produced using energy.
Okay. I'm going to just go through the rest of the slides for him. This is all his work, but just because he has a little bit of difficulty in projecting his voice, can I just go through these slides very quickly? So this is based on class size is one parameter, and pre-cooling that is talked about is the other parameter. So you see that just by using those soft information
fusing them with the smart solution where there is no occupancy, nothing is turned on, you could save a lot of energy. So in the next slide, this slide shows the baseline is in IIT in computer science department. The morning 9 o'clock, somebody will come, the security will come, turn on all the lights and fans and the HVAC systems in all the classrooms. And they are turned off only in the evening after the classes were over. That was the practice before. And then if you do, turn them off during the lunch break, then you saved some energy. These were all instrumented, verified, measured, verified in the computer science department. And the appliances, if you just actuate them based on occupancy, the smart, if you use that principle, you already saved 31% energy. You save it, the pre-cooling, if you use the pre-cooling factor, you saved 41. But you also used the smart schedule where you map the class size to the room size and use this pre-cooling effect. You could save up to 58% energy, and this was demonstrated in IIT Bombay. And also it only takes about 6 academic months to recuperate the cost of doing all these sensors and other artifacts that you have to come up with. So this is very interesting finding. Now moving on to example 2, that was a classroom space that was instrumented. Here this is an auditorium like here, FC Kohli Auditorium, where again, it was shown that just by reorganizing the seating arrangement, if it is not occupied completely, you ask people to move forward to the different zones and only use the lights and fans and the ACs in that zone, you could save a lot of energy. And it was shown that 30% energy. So we had to tell people, can you please move forward? Because people usually like to sit in the back rows, here, there, everywhere, right?
Ma'am, 1 minute.
Yeah.
1 minute.
So this is the second example that we wanted to show, and this is all the research that went on to even map the heat distribution in a big auditorium, and a mobile app was developed to do all these mapping, and without compromising on the user comfort, you could have a seating arrangement that was conducive to user preference also. So this is the example that we wanted to show. And finally, the smart door, which, if you have a lab-like space, you could identify who's entering just by measuring their height and weight. And you could turn on the appliances and keep their space ready when they entered the lab. All these things were developed in IIT Bombay in the Smart Energy Informatics Lab using this principle: sense, S for sense, M for meaningfully, A for analyze, R for remember and respond, and T for timely, which is smart, right? And so these are the useful CS concepts that were used. Lot of papers, lot of PhDs, master's theses, and many artifacts came out of the research that went on. And for the almost 10 years at IIT Bombay, and these are all the SAIL members. There is a very short video, with your permission, sir, if it can be played, we would like to play that.
Yeah, please.
Thank you.
This is the video.
In our endeavor to extend the use of unconventional energy sources, we have been exploring the use of building facades for harnessing solar energy. We are addressing the challenges posed by the shapes of modern buildings, curtailed radiations and shadowing effects to optimally determine solar potential, relevant policies and deployment strategies.
We should thank Professor Ram Tirtham as well as ma'am, who actually presented the work, and a fantastic video. Thank you so much, sir.
Thank you.
A fantastic work that you are doing. And I guess it's a very important concept of energy, reduction in our daily use. I think it's a fantastic thing that you do. I think we have to break for lunch, and I think probably we don't want to disturb him with questions. That's my personal view, but if you want to.
We can take.
you are happy to take
Yeah, I'll be happy.
Yes.
we can let the others go and we can talk to some group of people.
Yeah. So any questions, one or two questions, please, if you have any.
People hungry.
We are talking about smart things. I heard that smartphones, the greenhouse emission is comparable to the greenhouse emission coming from aircraft industry. So this is a thing that I heard recently. I was shocked to hear that.
Yeah.
So I think we'll be smarter if we use smartphone less.
Yeah,
Just one.
we don't use smartphones other than for getting picture of the terminal space. But one should remember that the smartphone does do a lot more of the activities that go on 10 phones. So we are getting a lot more for the $1 that we pay for it compared to anything else that we have seen in the past.
My request to the audience is to use smartphone less.
Yeah.
Any other questions? Otherwise, we will break for lunch. And we thank once again.
Thank you very much.
Professor Jan Pertham and ma'am who assisted the final slides. Thank you, ma'am, once again for your presence. And thank you.
She's a part of the lab, so I'm thankful for that.
This session is closed and we'll break for lunch now. Thank you.
Here is a formal announcement. We request you to proceed to the main guest house lawn where the lunch is arranged. We request the summer research scholars to walk up to the main guest house, and fellows and other associates would join on the vehicle, please. Thank you. And we assemble back at 2:30, please.
Good afternoon, everyone. It's wonderful to be here, and especially because it's my alma mater and my parent department. And I think after lunch, we are starting off a very interesting talk on nutrition itself from Dr. Anura Kurpat. He's a professor of physiology at St. John's Medical College in Bangalore, and he's an MD in medicine, and we look forward to hearing your talk. Thank you.
Thank you. So good afternoon. Thank you very much. I'm very happy to be at IISc. I hope there are some biologists in this audience, because I noticed you're one. Thank you. Great. Okay. Few and far between, but outnumbered by the physicists and mathematicians, I think. So I'm here to tell you about something that has been bothering me for some time. And I work in nutrition, and this is something that the National Institute of Nutrition puts out as to what you should be eating in your plate every day. And you will see that there is half that plate is vegetables and fruits, and only a third is cereals or grains like rice and ragi and wheat and so on. 1/3. Most of it is something else. But if you actually look at the food people eat, it's all rice. You go to a school and you'll probably find they're eating brown rice one day, red rice another day, yellow rice another day. It's all rice. There's hardly any diversity in that diet. And to that extent, it's worrying, because we keep thinking how many children are stunted in India, how many of them are not developing adequately. So the solution so far has been, well, if they're not getting the nutrients that come from a diverse diet, why not just put chemicals into their diet? For example, put supplements of vitamins into their diet, put some metals into their diet. So you get, adolescent girls getting pills that contain iron and folic acid. We get fortified salt, fortified rice. But nothing works, because, you go back to Aristotle, who said the whole is greater than the sum of its parts, and that applies to the diet, that you can't really split it up into, or disaggregate it into its nutrients, feed them all separately and hope that they would have the same effect of them being together in the diet. Now, the fact still remains that if you take a sentinel nutrient like, for example, vitamin B12, which I hope all of you know, vitamin B12 can only be found in sources that come from animals. You don't find them in plant foods. So animal foods are considered one of the diversifications. I know there may be some vegetarians who will disagree with me, but milk is, for example, an animal food. And so it's only vegans who don't eat vitamin B12. Now, if you look at the intakes of vitamin B12 in this country, they're terribly low based on international standards. So you'd expect, based on that terribly low vitamin B12, that 100% of us should be B12 deficient. But we did a national survey of Indian children, about 100,000 children, and we found a prevalence of B12. If you look at it here, at a max it went up to about 30% in some age groups in adolescence, but at younger age groups it was about 10%. And that was truly surprising for us. And here's the real kicker. You'd think that a lot of people would be clinically B12 deficient. Now, if you're clinically B12 deficient, you'll probably be anemic. You'll probably have pins and needles in your fingertips, because you'll have some form of neuropathy. Nothing. Nobody had any clinical signs. So this was what puzzled us as to, okay, if you say we eat such little amounts of B12, why are we not so deficient? So the questions we began to ask ourselves was, just for this sentinel nutrient, remember, this occurs with proteins, it occurs with other vitamins and so on, but I'm going to focus on B12 for this talk. And could B12 absorption, for example, from that minuscule amount that you get from milk or eggs or whatever you may choose to eat, could that be upregulated so that you really absorbed it all very well? Or could you be such an efficient person that you did not excrete B12? you hung on to it and you recycled it? Or could it be something else? Whatever it was, we needed a tracer labeled B12 molecule to figure out all these things that was safe for human use. The reason I say safe is that when we looked at the B12 tracers that were available on the market, these tended to be radioactively labeled with either 14 carbon or 57 cobalt. And that's a big problem. You go to any medical school ethics committee and they'll say nothing doing, you cannot give radioactive things to human beings. Sorry, go away. So what we decided was let's synthesize our own or biosynthesize it. So we got a culture of Salmonella enterica and we cultured it in our lab and we fed it with a substrate called ethanolamine, which was labeled with carbon 13, which is a stable isotope, safe. And once we did that, we were able to purify cyanocobalamin that was, or vitamin B12 that was produced by this Salmonella. We confirmed it by mass spectrometry. We did a lot of animal safety studies because you're working with cyanide and you're creating a molecule that was linked to cyanocobalamin. And finally, we got ethical approval to give this to humans, and we were able to do human absorption studies and then began our answering of all the questions that we had raised before. So we started with an oral 13C labeled vitamin B12 dose, and we gave it to humans, and we followed the absorption in the blood of this, and we constructed a 2-compartment model of the kinetics of vitamin B12, labeled B12 appearing in the plasma. And the old labeled B12 with cobalt, radioactive cobalt, gave a test called the Schilling test, which is used in clinical medicine and is no longer used, except if you're really sick. But 70 years after Schilling first published his method to measure the absorption of B12, we then did it ourselves with 13-carbon cyanocobalamin, and we found a bioavailability of about 50%. And note here that you'll see that the absorption occurs at a peak at around 6 to 7 hours, and that's because the majority of B12 is absorbed from the last part of the small intestine, what we call the ileum. However, just for curiosity, we kept sampling the blood, and we found, to our surprise, that there was a second peak that appeared of the appearance of labeled cobalamin. And that surprised us because where's this coming from? Well, there are different ways. One possibility is what we call an enterohepatic circulation, where B12 is absorbed, as you can see, from the ileum. It goes to the liver through the portal circulation, and there it will appear in the plasma where you can take a blood and you can measure it. But part of it gets re-secreted through the bile back into the intestine, in which case you would expect to see a second bump of a recirculating tracer. This is one of the problems that really bedevils a lot of the work we do with stable isotope tracers. So that could explain the bump, but the second explanation is a little easier. It is, well, if you could absorb vitamin B12 from the colon, that means it's gone past the ileum into the colon, then you'd get the same bump. So the question was, what do we do? And I was very fortunate to have a pediatric surgeon who's sitting here, Shalini, who she's one of my fellows, and she works a lot on several things around pediatrics. And she was very interested by this, and she suggested, why don't we just put some labeled B12 directly into the colon during a colonoscopy? I don't know if any of you know what a colonoscopy is, but it is where you put a tube up the backside of a person, all the way, as you can see, through the descending colon, through the transverse colon, all the way through the ascending colon, almost up to the cecum, which is where the ileum ends. And you can actually there, once you're there, you can squeeze in some B12, labeled B12. The point is that Shalini had to go to the colonoscopy lab, and there she had to talk to all the patients who are undergoing colonoscopy and get their consent to have this done, because the key was we needed to find healthy colons. So the gastroenterologist who's at the bottom here, Mallikarjun, would go all the way there, and if he said, yes, it's all good, clear, normal colon, we then inject the B12 into that person. If it was an abnormal colon, sorry, we weren't into measuring B12 absorption in abnormal colons. So this was done, again, we constructed a compartmental model, and you can't keep a patient after having a tube up his backside to say, now sit with us, give us bloods. They're going to say no. They're going to say, well, 4 hours is the maximum, we'll stay with you. So for 4 hours, we continue to take bloods, and you'll see there in that graph, you can see how labeled B12 appeared in the blood, meaning it was being absorbed, and about 8% of a 5 microgram dose was absorbed. And that was fantastic for us because it showed that that could be a reason for that second bump. I'm not saying enterohepatic circulation doesn't occur. It could, but it looks like this might be a major reason. There was one problem we had, and we still have, which Shalini is actually solving for us, and that is that when you put a needle into the vein of a person, you're measuring the blood that got past the liver. But once the blood goes through the liver extracts a lot of nutrients out of it. We call this first pass absorption. And what appears in the plasma is what the liver doesn't want. So you really don't know how much was absorbed. So we need to figure that one out. So we're doing that, and Shalini is actually, you can do it by giving the same labeled B12, give it orally and IV. And if you can give it orally and IV, you can actually work out mathematically what is the first pass disappearance that occurs in the liver. This is an experiment that was done with riboflavin. So what we are doing is we have this really smart guy who came and joined us from IIT Madras, who's some kind of biotechnologist, and he is synthesizing, biosynthesizing 2 types of labeled B12 for us. One is an M+4 B12, and the other is an M+1. So on a mass spec, we can actually differentiate them. One will be given orally, and one will be given IV. And this was where we really began to see that, well, it looks like we're changing some dogma, because if you go to medical textbooks and try and look at it, basically the dogma is this, that once you're past the small intestine, that's it, you're dead. You're in a zone of excretion. Nothing gets absorbed there except water and maybe some salt and maybe some other small molecules, but not nutrients. But the fact is that we think that this dogma has to be reversed, and this is beginning to appear in textbooks from the papers we have written. And there are several bugs in the microbiome that can produce all those vitamins that you can see there. And for B12 particularly, in vitro, there are experiments that have shown that the human gut biome has the ability to produce up to 0.6 micrograms per ml of whatever brown stuff is in the colon. So it's a lot. So Shalini actually then applied to ICMR, which came out with this grant RFA, which was what they call the first in the world. It was to do research that no one else was doing in the world, do it for the first time. And so her point was, let's trace what these bugs are doing by offering them labeled substrates to ferment, and then see what nutrients they produce. And so she got this grant, the first in the world. They give you up to 15 crores to develop it's like you keep getting more and more money as you think of new things to do. So right now what she's done is she has introduced 13C sugars into the colon. Now if you put 13C colon orally, it will never reach the colon, it will be absorbed. But you can give 13C cellulose, and that reaches the colon, it gets fermented, and she's looking at 13C B vitamins in the plasma and in fecal samples, which are not really the best thing, but they give you some index. So this is a sort of experiment she does. She gives 13C cellulose once, and then she kind of follows them for 3 days, taking blood samples every so often. And this is what she's found on something like 15 subjects, that there is a production of of B12 that appears in the plasma. So I think there's no doubt that if the cellulose reaches the colon, this can be produced, and you will get B12. And when you model it using first compartment kinetics, we find that you absorb about 1 microgram of B12 per 2 days. Just in context, your requirement is about 1 microgram per day. So you can get up to half of your requirement through this. And now we are actually looking at the microbiome and trying to look at the abundance of the microbial B12 synthesis genes, so you can see the pathways on that side, and we have mapped all those genes here. And so there is evidence that there's an abundance of genes, and then we've actually mapped those to specific bacteria. And you can see that these are the bacteria. This is just 9 subjects. We've got a long way to go. But my point is that we are on the way to actually figuring out which bug produced it and so on. And so I'm going to end here. So there are several necessary and several unnecessary questions with this. The necessary questions are, I mean, what else can the microbiome produce? So Shalini is actually looking at riboflavin, thiamine, pantothenic acid, folate, I mean, a number of B vitamins. We could look at vitamin C as well. The important thing is, with what precision can we measure the appearance of these vitamins in the plasma? How much of first pass did we miss? So we need to have 2 isotopes, IV and oral, which is what she's doing with the first. First in the world is not just B12, it's several vitamins. And more important, how can we measure functional outcomes? I think there are other nice questions. For example, what makes the altruistic bacterium? Because why on earth would a bacterium synthesize large amounts of vitamins and then secrete it? What told it to secrete it? What is the crosstalk? Is it a host-based thing? Is it a microbial ecology? These are really interesting questions that we look for in the future, but there are unnecessary questions that I get asked all the time. I hope you won't. It is, do we need to eat food at all? No, we do. We certainly do. There's a silly season for all science, but I hope we don't go there. Thank you.
Thank you so much. I think you conveyed such a beautiful piece of work in such an amazing time. And lots of questions in my mind, but first the audience. I think Thelma and yeah.
There are all these probiotics that people keep recommending that you have. Is there a way of designing a good probiotic soup that you can introduce, for those who are deficient in B12?
Yeah, actually, the reason Shalini got, she's sitting there, by the way, the one in the yellow.
Oh.
The reason she got the first in the world was she said she would do this. She would design a probiotic for public use, because our biggest problem is this, that we go and dump these chemicals into the food of people, large amounts of iron, for example, which completely changes the biome, and to my mind reduces its ability, perhaps, we have to check this, to synthesize these things, because you get ferrophobic bacteria that hang out, or ferrophilic bacteria. So you're right. So our aim is not only to produce the probiotic, but a prebiotic. Figure out a mixture of the food that it likes, because there are different fibers. And we're thinking that one of the cheaper ones to give is a fiber called inulin. And we're trying to investigate that as well. So thank you. Yeah. You should get the first in the world prize.
Yeah, the other question which I had was that you talked about children to start with in your survey that you found. So do you assume that they really had a very healthy microbiome? And that is why you really kind of got such a high percentage of B12?
Absolutely right. Thank you for that. They are big assumptions, because when you do these national surveys, it's kind of, you know what survey is going on for the caste system in Bangalore, where they just go and stick something on someone's door and say, we survey. You don't get much time. So we could not get stool samples, but there are many issues around B12. One issue that some very good investigators in Vellore had suggested was many people get their B12 from sewage. So you drink dirty water, but look, if you drink sewage, you will get B12. You may get many other things, but it was a suggestion at the time that could be one way. But now, as we have cleaned up our water, it's unlikely. The other is that maybe people eat more non-vegetarian food that they let on. Most people, if you ask them, they say, no, I don't eat any. And many people, when you go and ask them, do you eat well? They say, no, I don't, because they hope they're going to get a handout. So there are lots of psychological issues around this, but thank you. I can't answer your question, but I think they had a reasonable microbiome.
you know, you have to evacuate
Very
that
good,
data. So
very good.
doesn't that potentially affect the results that
No.
that you get?
No. The reason is, the question we are asking was, does the mucosa absorb the labeled molecule? Not, does the microbiome produce that molecule? So when we did the colonic experiments, it was clearly only to show that there was a potential for absorption. Once that's done, what Shalini is doing is she's putting cellulose into a non-treated colon. You're absolutely right. If you look at the colon that is undergoing colonoscopy, it's brilliantly clean. But that's not the normal situation. So the only way to test whether there's fermentation is to have a non-cleaned colon, just give cellulose to just free-living people and track whether there's this absorption.
Thanks for fascinating information. I heard about 5-6 years ago that insulin is secreted by a group of bacteria. So the tablet metformin is actually a food for that group of bacteria. That was Nature article.
I wish I could answer that. Shalini, do you know anything? No.
I have the reference and so on. I will give
that's
In fact,
fascinating.
I heard the talk by that Norwegian gentleman who came to Chennai and gave a talk on diabetic center. So I talked to him. So it's a Nature paper.
I'd love to see that, because I don't know if there's any insulin absorption that could occur. I have to look at that.
So the bacteria produces insulin.
That's fine.
And the metformin is a food for that bacteria.
That's fine. How does the insulin get into the body is my question. That's what I think. I'd love to see that.
Sure.
Thank you.
Thank you so much. Just a small question that would the vitamin B12 levels need to be reassessed as to what would comprise a range for vitamin B12, because that's what you started your observation with, and would then getting a lot of people supplemented with vitamin B12 be not needed?
It's not a good thing. Please, for all of you who pop pills of multivitamins, not a good idea. Just eat a diverse diet. There are people who have died because they take too much of multivitamins. So please be careful. However, you're absolutely right. The diagnostic cutoff for B12 is a matter of great debate. Different countries have different levels. In India, we have not yet decided what that level should be. So we just follow what others take.
I think we do that for everything, for diabetes and all, and high time, somebody took it up. ICMR has been talking about it for 20 years, but there are no values in India.
That's
because
true.
the diet of Indians are very different from European diet. And
We don't even know what
still
India
follow.
eats.
Yes.
That's the problem.
Yeah.
Somebody told me, some doctor, don't be too clean. That's the secret of Maya.
Absolutely. Give yourself some immunity, some resistance. Yeah.
Thank you
Thank
so
you.
much.
Thank you all.
Thank you. So we have the next talk from Dr. Priyanka Grover. She is an associate professor in Shivnadar University, and she's going to talk about subdifferential calculation, approximation, and orthogonality, a subject which I don't understand, but I hope to understand from you. Thank you.
Thanks. Very kind of you.
Okay, good afternoon everybody. First of all, I would really like to thank the Academy for this wonderful opportunity in front of this wonderful audience. This is a huge shift from what we were just hearing. So, but I promise that at least the first few minutes will be very familiar to almost all of you. So, right. So I begin with something very, very simple. We all have seen that, orthogonality in Rn. Dot product we understand in Rn. In Cn, We take conjugate linear in the first coordinate, linear in the second. Then with these dot products, there is a length of vector, which is this. In Rn, it's mod x1 square plus mod x2 square plus mod xn square to the power half. And orthogonality is just inner product of xy equal to 0. So these are two orthogonal vectors. We all have seen that. You can tilt them a little bit if you like, but this is the beginning point of our study. Okay. So this is a simple situation for us, and quickly, because I will soon go into my matrices, but I'll come back to vectors just in the next slide. If you have the space of n cross n complex matrices, then you can still define an inner product. As soon as you have an inner product, which is the dot product, using the trace of matrices, again with the same procedure like we just did, there is a norm, that is the length of a matrix, which is derived from this inner product, this dot product, and there is a simpler way to look at it. So if A was this matrix Aij, entries A11, A12, A1n and so on, then this norm will precisely look like summation of the mod square of all the entries. So that's something that we all understand, and then we can define orthogonality with respect to this inner product, which is just trace of A star B equal to 0. So that's our simple situation. Okay. Okay. So one term in my title was orthogonality. This is the simplest orthogonality that we understand. Next term was some approximations. So here is some motivation why we study approximations. There are lots of other motivations, but this is just one. Given in a usual vector space course, linear algebra course, we understand that whenever we get linearly independent vectors, Gram-Schmidt tells us how to orthogonalize them. Okay, I see a lot of nodding heads from the students, so that's good. Right. The problem is how to find the one which is closest to your beginning vectors. Okay. And in chemistry itself, in some models, quantities are expressed as orthonormal vectors. Okay. But then experimental observations give us which are not orthonormal. So I want to find something that is closest to my observation. Right. And this was done by Loudon through his orthogonalization process. If you have heard about it, good. If not, then here is a very nice article by my supervisor, Professor Bhatia, in Resonance, where he explains all this and its connection. Okay. But let's skip to our general thing. Okay, so quick thing, answer to that question. Gram-Schmidt wants us, gives us an orthonormal basis out of linearly independent vectors. Question was to ask which one is the closest. Matrices are close to our heart, so Gram-Schmidt can actually be written as this particular formulation in terms of matrices. So now my initial vectors A1, A2, An, I look as the columns of A. So if they are linearly independent, my matrix is invertible. And then Gram-Schmidt, what it actually does is it gives you a unitary matrix Q, which is basically your orthonormal basis, and an R, which was the remaining what you get in the process of orthonormalization. And if you impose this condition that R should be an upper triangular matrix with positive diagonal entries, then this is unique. This particular factorization is unique. Another interesting decomposition of an invertible matrix is with respect to the polar decomposition. So there are some terms. U is again unitary, orthonormal columns. P is a positive definite matrix. Okay. And out of all these unitaries, actually this is the unitary which is the closest to A. So that has been already shown in literature, and this is the one that Loudon actually found. Okay. It boils down to this in matrix theory. So that's the beginning of motivation for why to study approximations in matrices. Okay. Now this is a very, very simple norm for us. So I'm going towards more mathematics now. So if any matrix A can be decomposed as singular value decomposition. So there you get two unitaries and a positive diagonal, non-negative diagonal. And then this was my, with respect to these are known as singular values of A. And then this Frobenius norm is nothing but the Euclidean norm of the singular values. But then there are more interesting norms on matrices. The supremum norm, the spectral norm, operator norm, then the Shatton P norms, numerical radius, Key-Fahnke norms, and so on and so forth. So the idea does not stop at inner product for us, and that's the bottom line of everything. So here is one more quick thing. In general, the problem is this, that if you have a subspace, there is a vector outside, you want to find the closest vector W here, which is the closest in this setting. So in our Rn Cn case, we have this inner product, everything is very nice, and the orthogonal projection got by that is precisely the one that is the closest. But this norm, I don't want to stick to this norm, but this norm was coming from an inner product. Orthogonality was defined via an inner product. I want to escape that and go to more general settings. So this is the best approximation that I just said. Okay, so now I want to go to more general settings. There are more norms on vectors, more norms on matrices, which are more practical, which come from various applications here and there, in quantum mechanics, everywhere. So I cannot just stick to this Hilbert-Schmidt norm, which was coming from the inner product. So when I ask the question of best approximation, one question is, when is 0 the best approximation to x in my previous setting? That means I have this relation. When there is an inner product and the norm was coming from an inner product, then this is precisely when you have orthogonality. So now this becomes my new definition of orthogonality, escaping the inner product, but just with the help of the length of the vectors. So norm is the length of these vectors. Okay. So when I change norms, this still makes sense. Inner product is gone. Okay. More generally, if I want to stay in vector subspaces, then I would ask this question. Right. So this, again I repeat, when is 0 the best approximation to W from x? Okay. So I will say that x is, in the next slide, I will say that x is said to be Birkhoff-James orthogonal to this subspace if this condition holds. Okay. And this was initially done by Birkhoff and James, therefore the name Birkhoff-James. Birkhoff initially did it only for R3, but James really truly generalized it in norm-linear spaces. Okay, so here is my situation in Mn, I am back in Mn. Remember I had an inner product, but this is the operator norm now. So for two matrices, Bhatia and Shemrel in 99 had this remarkable result, which has these days a lot of studies going on with just this result in the past decade. So they said that A is orthogonal to B in the Birkhoff-James sense, now in this norm, if you can find an underlying unit vector where A attains its norm and Ax, Bx are orthogonal in the usual sense. So now Ax, Bx are vectors in Cn. Okay. So it connects a more complicated Birkhoff-James orthogonality to the standard orthogonality in Cn. Right. So here is where they did it. Okay. So what we did initially was, with Tirtho who is sitting here, we developed a new method of looking at this particular problem via different lens. So this was a very simple idea. So remember that if x and y were vectors, then this is, and suppose I was in real space, which is easier to understand, then my t would be coming from reals. Now if I look at this function which takes t to norm x plus ty, then saying that x is orthogonal to y would be the same as saying that f is attaining its minimum at 0. But then this is attaining minimum at 0 is a calculus problem. The only problem is my f is not differentiable because norms are not differentiable. But then these tools of convex analysis come into picture because norm is a convex function. And that's where the idea of subdifferential comes in. So here is the idea of subdifferential. Here is a picture which will make it more clear. Definition you can read later. Okay, so if everything was differentiable, for example, at this point I have one single tangent. Now this is a convex function, and suppose at this point there is no differentiability, then I would have multiple tangents. What I am really doing is collecting them and forming a set which is known as the subdifferential set. Okay. Now this idea really helped us, because when I say that f needs to attain its minimum value at a point, it just means to say that 0 should be in the subdifferential set of f at that particular point. And many mathematicians have studied this subdifferential set for various norms, and we did it further for our own cases whenever we needed it. So that was the main idea that we developed and are still using it, because it helps us getting various very strong results in several settings still. So, okay, sorry. Okay. The main objective was that earlier only orthogonality was known from, for example, A is orthogonal to B was known. But what if I want to say that A is orthogonal to the whole subspace of Mn? Okay, so this problem has been studied for quite some time in general. I mean, approximation problem, finding the closest, for example, in trace 0, the subspace of trace 0 matrices, we know that this is the closest. In the space of real subspace of Hermitian matrices, we know that the real part of A, which is the Hermitian part of A, is the closest. But then the more general problem was actually solvable by this idea of subdifferentiability. So we could actually use that idea and say something very strong in terms of orthogonality as well as approximations and several more. So this was again an old result. So we said that if for any subspace you can find a similar characterization, but this time you will not get a single vector, you will get a density matrix, okay, which does similar things. So A star AP is norm A square P and AP is in W per, and then there are more conditions on P. Okay. One of the implications was that this result of Audenarth had a very simple proof using our previous result, which I am not, proofs I am not presenting here, but here is the what this result actually does is that it relates the distance of a matrix from this particular subspace to the maximum of quantum variances. These are quantum variances of A. Okay. Okay. So Bhatia-Shemirel theorem again looks like a simpler version of our result in terms of density matrices, which is just presented here to have a look that something is similar. Okay. These are also related to another area which is now coming up as minimal matrices. What they do is that they actually allow us the description of minimal length curves in this flag manifold. Okay. So the existence of minimal matrices allows some description of these minimal length curves in this particular manifold. But minimal matrices are nothing but really our relation of orthogonality in a very special case. So so here A should be Hermitian matrix and D is nothing but the subspace of diagonal matrices. So whenever this relation is true, so from that area also this is coming in, that A is said to be minimal if this condition is satisfied. But in our notation it is nothing but saying that A is orthogonal to the subspace of diagonal matrices. So again this was a result that was done for minimal matrices, but then it again looks like a particular case of our result. So that strengthened it. More general settings for people who can understand. So again quantum mechanics wanted to look at algebras of physical observables, and those structures brought up C-star algebras. So we want to extend our whatever we have known to these settings, and this we did in 2021. So if A is a unital C-star algebra over any field with identity, and assume that C-star subalgebras of A also contain identity, then similar notations are there. B is a subspace. Okay. Distance is this. Then if you have this set of states, I will just take 1 minute, slides are almost over. Then you can have a similar thing, that if you can have a best approximation characterization in terms of the states. And in the next slide you will see that it is something extremely similar to what we have just seen in matrices. Matrices are a specific finite dimensional C-star algebra. Block diagonals are subalgebras, C-star subalgebras. So what we just said in the terms of Birkhoff-James orthogonality is that if you take a subspace of a C-star algebra, an element of a C-star algebra outside the subspace, then it's orthogonal if and only if there is a phi from the state, again at A star A it attains norm and at A star B it's 0. And there is a semi-inner product with respect to every such phi, which is precisely given by phi A star B. So it's exactly the same as we were doing in matrices, but only difference is this time it's coming from this phi. So again this was done recently. Yeah, that's where I will end. Some more work in this direction has been done in these recent papers, which I have not talked about much, but this is the survey article that if you are interested in, you can have a look. It has almost everything related to that. Okay, thank you.
Thank you so much. Any questions?
Yeah.
Use Fock space of antisymmetric wave functions. So does your theorem apply there?
Yes, it will.
I see.
It will.
For symmetric as well as antisymmetric.
Yes, because it's for a general subspace. Our theorem is for a general subspace. More conditions can be imposed on that density matrix given the structure, but it will work. Yes.
Any further questions? Thank you.
Okay, thank you.
So we have the next talk by Dr. Parthasarathi Mukhopadhyay. He is formerly he was associated with IITM in Pune. That's the Indian Institute of Tropical Meteorology, and now is currently at the Department of Earth and Environmental Sciences in IISER, Berhampur. So.
Okay, thank you. So I take the opportunity to thank Indian Academy of Science, my gratitude for inviting me and asking me to share some of the results. Although as Madam said, Chairperson, that I retired from IITM, but what I will share here is our latest work that just before retirement I could complete, and it is now formally being inaugurated by Honorable Minister and so on, and now it is being implemented across India as a Bharat forecast systems. Okay, and so the title and of the talk is an indigenous kilometer scale model to improve monsoon extreme precipitation deadlock. So I will try to argue what is the deadlock, why is the deadlock, why on earth there was a need of a kilometer scale model. If we would not have done this, what would have happened, and so on. And there is not a very big group, but a few scientists who all worked for almost 5 years to complete this model. We started the work in 2017 and got it completed by 2022. Evaluated the model for 22, 23, 24, and then handed it over to IMD in 25. This is the sequence. Okay, so this is the I will go to introduction. So this is the paper. Paper is, and the good thing is everything is free. This paper is free. Anybody can download. The model is free. Anybody can download the model. If you have a HPC, you can run it, and the data also will be free. So everything is free. The code is free. So that was a challenge actually, because see, always we normally adopt model from US or some other places, and now it is becoming more and more difficult. Models are not getting free. So there was a need actually. So the students can actually do experiments using even National Supercomputer Mission or any grid with this model. So just this is a background. So what are the key challenges of numerical weather. NWP means numerical weather prediction. By the way, I was told that the slide should be very general, so there is no equation, no physical, chemical, mathematical equations, although behind the scene there are many equations, okay, and anybody can understand, even arts, commerce, science, anybody. So this is philosophy actually. This is a paper written by Peter Bauer of UCMWF, published in 2015 in Nature, and he said that this numerical weather prediction is a quiet revolution. And now what we are seeing nowadays is AI/ML. We say another quiet revolution, okay, which possibly will replace this numerical weather predictions. But anyway, this figure basically explains very nicely the complications. Okay, these are the systems which we all come across in various time scale and space scales, like convection, storms, tropical cyclones, okay, monsoon, and so on. And what you can see is that if I increase my model resolution, my model complexity increases, okay, and then so many other things comes. Computing increases, okay, coupling increases. Coupling means you have to then consider ocean, you have to consider land, and so on. But if you consider turbulence, okay, your ocean, etc., may not be so much of importance to be coupled, okay. So this actually in one figure, Peter very nicely summarized the complexity that we are going to deal with. The second slide, there was a virtual experiment called Year of Tropical Convection, paper published in Bulletin of American Met Society in 2012. And here actually the author Mitch Moncrief, they explained from observations, and you can see very clearly that it is diurnal scale. I mean, you can see that the temperatures, what we experience in the morning and what we experience in the noon and what again we experience in the nights are not same. This is what we call diurnal. The rainfall, again, it's not same. What we, in many places we find rainfall happens in the late evening hours. Some place in India we experience rainfall in the early morning hours, and so on. So these daily, sub-daily variations are considered to be diurnal. But and this is seasonal cycle. What happens in June, July, August, September in the total season. But very interestingly, these are all linked. Okay, so if I try to predict the seasonal cycle, I have to keep in my mind even the variations in diurnal scale. So this makes the whole thing very complex. That you have to model a system, which has a connections from sub-daily scale within an hour to a month to a season. Okay, this makes the whole physics very complex. Okay, actually one of my physics teachers told you will never be able to solve this problem. Okay, yeah, but anyway, so we are still trying that. But before going to my kilometer scale, I always show this figure to all my students, and here also there may be many students. So this was the first history when we started this numerical weather prediction. Von Neumann standing here, Jules Charny. It's 1945, ENIAC computer in Princeton, right? So this was the history, and this was a recreation of the forecast. I mean, the paper that they published. This was done by Peter Lynch in 2008 in BAMS. So what you see here is that this is the initial analysis, okay, and this is the verifying analysis. Basically, you can see it is the observations. Okay, this is the initial observation. This is the final observations, and you can see there is kind of congested line. So this, you can think of that this is a system. It's a low pressure or depressions or anything. Okay, weather disturbance that has moved here. Okay, and what they tried is a very simple model, just 24-hour forecast. Okay, and this is the difference. Okay, the red lines are difference. Okay, so what you can see is that and this is actually the forecast. Okay, so you can actually see that their forecast was not that great, because in actual verification it is here and here it is left of the line, but still in 1945 they have done a great job. Okay, but there was an error that you can see very clearly. Okay, but then in 2009 we published this paper, and we were trying to see not exactly that similar to what they did, but we were trying is somewhat similar. So monsoon we were trying to see. We are trying to see the daily convergence. We know when monsoon comes, the wind has to converge to bring the rain. And this is what we have plotted here is a upper level divergence. This is a mass continuity. If there is a lower level convergence, it has to diverge in the upper level, right? So you see the divergence in the upper level is propagating northward. That only brings monsoon, right? And this is the lower level convergence. You see lower level convergence also propagating, upper level divergence also propagating. This means your wind and rain and everything is propagating northward. That's how we get rain, right, in monsoon. But in just 24 hours, okay, this is the forecast, okay? You don't see the propagation at all. So it is in the year 2006. You see, so this is one deadlock, okay? 1945, you just saw, and this is in 2006. This was a model by US, okay, NCEP GFS. So we noticed it very badly. And this is a paper in 2020, okay? And here what you see is a series of, okay, climate models. This is CMIP 3, this is CMIP 5, this is CMIP 6. CMIP 6 is the last AR6 report, the climate IPCC, okay? And you see what is plotted is mean error of rainfall, okay? And the green line means excess rain and the brown means the deficient rain. What you can broadly see in all, right from CMIP 3 to CMIP 6, okay, all oceans are raining more, all lands are raining less. But we live in land, right? So where actually disaster strikes, and so lands are raining less and oceans are raining more. This is another deadlock. The deadlock is continuing, right? So, and this was another paper we published in 2010, just using different physics. I'm not going into the detail. This is observations. Again, you can see rain, monsoon doesn't come in a continuous manner. It comes in epoch. Sometimes it rains, then it's break, then again it rains, and so on, right? We call it intra-seasonal oscillations. You can see it here, okay? There is a epoch here, there is a epoch here, and so on. But you see the model. It keeps on running, okay? You don't see the epoch, okay? So why this deadlock, okay? And what's going wrong? This is the next question. Naturally comes to our mind. So this was an error, actually. We're back in 1974. We actually celebrated 50 years of this last year, okay? There was a conference in US. So this was proposed by Arakawa. He was in UCLA. He passed away in 2020. Q. Arakawa and Wayne Seward. He was in Colorado State. What they said is a closure, okay? And all models till today follow very honestly this closure. And what is that closure? The closure is that a large-scale process will control your moist convective process, and the feedback will go back to large-scale process. To be more, little more clear, the same diagram with little more background, detail. The large-scale process is nothing but some example is monsoon, which is bringing the moisture. Okay, if you add moisture in the atmosphere, it will create instability because it's very simple. The molecular weight of water is 18 and molecular weight of air is 30. Okay, if you replace the lower level by 18 and upper is 30, the top heavy system is unstable. So that is nothing but destabilizations. Okay, so destabilization is created by the addition of moisture. Destabilization means instability. How do we measure instability? Is by convective available potential energy. This is a term we use in climate science. It's called CAPE. Okay. And so, but then atmosphere cannot remain unstable. We know in physics it has to come to equilibrium, right? So moist convective energy produces kinetic energy. That's what we call it weather. We call it storm. We get strong winds, right? So it generates kinetic energy. That's weather. Okay. The result is warming and drying to bring the atmosphere back. That's a feedback. The unstable atmosphere bring it back to stable. Okay. So what he said, Arakawa and Schubert, that this process that generates the instability and the process that consumes the instability, they are in equilibrium. So the rate by which the instability is generated and the rate by which it is consumed, they are in equilibrium. Example, you are driving a scooter, bike, car, anything, right? And when you are driving at certain speed, it requires certain rate of fuel, right? So the rate of supply of fuel and rate of consumption of fuel has to be equal, right? If it is more, then it will spill. If it is less, it will stop. So that's the equilibrium. But the fact of the matter is, what we found nowadays, that this equilibrium assumption is failing. Okay, it's not realistic. That we have published a GRL paper, and these are the models. All gone into CMIP 6. Okay, they all use the same assumption. This is a deadlock. Okay, and unfortunately, we could not find another convective closure till date. We don't have any closure. As a result of that, you could see this is a diurnal variations of rainfall and outgoing long wave radiation. Outgoing long wave radiation is nothing but the top of the cloud radiations. Okay, so if the cloud is top, you will see the temperature is low. Okay, and you see here we plotted a scatter diagram. So early morning, okay, cloud is not so deep. Okay, but by the time it comes to 5:30, the cloud is deep because it is reaching to 210 Kelvin, right? And the rainfall also is increasing. So there is a variation of cloud and rainfall. But what the model is doing throughout the day, it is continuously raining in the same. That's what is reflected in all other previous figure. Okay, so that's what is seen here. Okay, so cloud is continuous. It remains same. It doesn't grow in the model. Okay, okay, I'll skip this. So this is what I show it to my students, is that how cloud actually, we have studied in our physics class, geography. So cloud, the moisture goes up, condense, rain falls. Okay, but you see the box, it's a kilometer scale box. So if I want to come very near to the cloud and get rid of that inaccurate closure, then my resolution has to be 1 kilometer. Okay, this is an example. Okay, so Arakawa later on in 2013 he realized, okay, and he said that one of the possible solution is you go to global cloud resolving model. He himself prescribed in 2013. Okay, and so but before going to the model, is there any societal need? Okay, the question is yes. There are multiple studies by now. First by B.N. Goswami 2006, then by Rajivan et al. 2006, then my friend Roxy et al. In 2017. All are unanimously suggesting that extremes are increasing. You and me also are agreeing. You and me also are experiencing extreme rains, extreme heat. Everything is increasing, right? And the benchmark, devastation, heavy rain is the Kerala event of August 2018 and 2019. And what we noticed is that that was a rain when the rainfall deviation was something like 30, 40, 50 sigma. I really don't know there is any system in science that deals with such a variability. So this was the rainfall, and you can see by all the GFS, ECM and NCO and model, UK model, Europe model and US model, none of them could capture this rainfall at all. Okay, I'll skip this. Now this is AIML model. Okay, this is by NVIDIA ForecastNet. This is by GraphCast, and you can see they are not capturing this extreme rain either. Okay, so we should not be in a idea that the AIML can solve all my problems. Okay, and because I am in Berhampur in 2023, I saw this enormous event in Bhubaneswar by afternoon 2:30. The rainfall, there was no rainfall. By the time I come in evening, it was something like cloudburst. Okay, this is happening very frequently. There was a paper by Rajivan et al. They are also documenting that extreme heavy rainfall is increasing, and so that's how this is the motivations that if you increase the resolution, go to a cloud resolving scale, you can possibly resolve this event. So keeping this in mind, we developed this grid, which is called octahedral grid. No time to go into that, but you can at least appreciate that we come close to the equator, the number of grids increases, so we have the better chance to resolve the high frequency waves. Okay, there are many advantages. One advantage is it takes less time. It is scalable. If you have more computer nodes, it can run even faster. And this is the just schematic where we show this is the grid. Then we ran aquaplanet mode. Then we added the land. Then we added the orography. Then we added the vegetations. Then we get the full 3D model. It took 5 years. okay, 17 to 2022. Okay, this is one result where you can see that these are all spurious rain. Actually, forecaster will think there is very heavy rain. These are all errors. Okay, those errors have almost gone in this model. Somebody was talking about Saran other was talking about the tails. This model actually captures the tail pretty good. Okay, and this is the the one case of heavy rainfall. You can see even after 5-day forecast, it is capturing the rainfall, where the current coarser model is not able to do that. And a tropical cyclone, it is particularly doing really good. Okay, the errors in tropical cyclone has drastically reduced, where it is 298 kilometer. Here it is just 50 kilometers. So, yeah. So my concluding remarks is that it is there. I will not read it. So I will end it. And this is the photo. There was a ceremony in Delhi. So Honorable Minister and Secretary, Director General, they handed over. So this model is currently operational across India. So I stop here, and thanks a lot.
Thank you so much. I think it's also well within the time, and it's open for questions. I'm sure there would be few. Any, yeah.
In terms of weather prediction.
Oh, sorry. Yeah.
In terms of weather prediction that is used locally, are they used in various places in India, your model?
Yeah, now this year they are going to use this model.
Not yet, I see.
Yeah, it has started. They have started using it from 1st June itself.
So then we can rely on the weather prediction. Thank you.
Yeah.
So,
Sorry.
thank you. That was a nice talk. I was just wondering, what is the kind of computational requirement? So, say if you want to do simulation for 1 day's prediction, how long does it take on the computer, and on which type of computer do you use?
Okay, actually you can check our paper. There we have given a detailed graph, but currently we have a petaflop machine in IITM. In that machine, this model is taking around 3 hours for a 10-day forecast. But there is a detail of nodes and computer processors, etc. I can share you the detail.
Any further questions? Yeah.
So in the model, over how wide a span of geography does the input data come in to make the prediction?
From where?
Yeah, from where all does it come from? The entire globe? Or?
Yeah, entire globe. Yeah. So we have a center in Noida. So they have a receiver, and in this domain there is no boundary. All country, they share honestly their data. It is shared in GTS, Global Telecom System, and it is received in a coded form, decoded, quality controlled, and then assimilated, and then the initial condition is prepared. And then this model story starts.
But the model predictions are specific for India, or they are also for the entire globe?
For entire globe, but because we are too obsessed with India, and I mean reasonably so, we always highlight India, but it is global.
Thank you so much.
Thank you.
So does it predict what's going to happen? Because I've been in Rajasthan for the last 4 years, and every year there's more and more rain coming.
So madam, I give you an honest answer that no model can predict such a complex system 100% accurate, but definitely this model performs better than what we have earlier. And one metric you see, I always tell that earlier you used to see Times of India, RK Lakshman every day a cartoon for whether man or woman. But now cartoonist doesn't make so many cartoons on weather, so perhaps we are performing better than what we used to do earlier.
Thank you so much. So the next speaker is Dr. Mohammad Naseem. He is from IISER Behrampur. He is an associate professor of physics at IISER, and he did his PhD from NISER Bhubaneswar. So he's going to talk about heavy ion collision, window into QCD phase structure.
Good afternoon, everyone. First up, I would like to thank the Academy for giving me opportunity to speak here. So I'll talk about a heavy ion collision, which help us to probe the QCD phase structure. Okay, so this talk has two parts. The first part is introduction. So I'll try to introduce this research area to the general audience. The second part, I will discuss the result where my contribution will be there. So as you all know that the visible matter is made up of atom. Everything in this room is made up atom. And atom is further made of nucleus and electrons. Electrons is a truly fundamental particle. You cannot divide it further. However, this nucleus is made up of proton and neutrons. Okay. And the neutrons and protons are also not a fundamental particle. They also made up of quarks. So each proton is made up of 3 quarks. Neutrons are also made up of 3 quarks. So like electrons, the quarks is also a fundamental particle. As per today's knowledge, you cannot make it further divide it. So there are 17 elementary particles in the standard model of particle physics. We can say these are the building block of our universe. Now if we talk about the quarks, so there are 6 types of quarks, namely up, down, charm, strength, top and bottom. And they differ by their masses, their electric charge, and they also possess a color charge, you can say colored degrees of freedom. And how they interact? The quark interact by exchanging a gluon particle. This is called the exchange particle. It also contains a color charge and it's massless. And the quantum theory that describes the interaction between the quarks through the exchange of gluons is known as the quantum chromodynamics. In short, it's a QCD. Now, according to the QCD, the potential energy between the two interacting quarks has 2 terms. First term is a Coulomb-like term. It's inversely proportional to the distance, and it's the attractive term. And second term is linearly proportional to the distance between the quark. So if you plot this potential as a function of distance, as you can see from this here, when the distance is low, the first part will be dominating, that is the attractive part. As the distance is increasing, the second term will be dominating, the repulsive part. Okay. Now what happens if you try to separate 2 quarks which is bound within the hadrons, like here, there is a meson, it's a quark and antiquark pair, and if you, by giving energy, if you try to separate the energy with the increasing distance, the energy between these 2 quarks will increase, and you create a flux tube which contains a lot of energy, and this energy will be get converted into mass, which will create a new quark antiquark pair. So eventually you started with 1 meson and you end up with 2 new mesons. So you don't get a isolated free quark. So the quarks are always confined within the hadrons, and we are interested to study a matter where quarks are deconfined. Okay, so how to do that? So if you look back again here, the QCD potential, this alpha S is a strong coupling constant. It's a constant, but actually it's not a constant. You can show the alpha S changes with changing the momentum transfer in the reaction, or you can say the energy transfer. So it is actually decreasing with increasing the momentum transfer. So it was predicted that if we create a high temperature and or a high energy density, then the alpha S could be very small, then this potential could be very weak, and you may create a deconfined quarks and matter that gives rise to a new state of matter called quark-gluon plasma, and this phenomena is known as asymptotic freedom, and it was the subject of Physics Nobel Prize in 2004. Now how to do that? How to create the high temperature and energy density in lab? So before that, we like to go the further prediction from the QCD. So this is a QCD phase diagram. When we say the phase diagram water comes in our mind, right? We know at what temperature and what at pressure there's solid, liquid or gas. And if we talk about the phase diagram of water, the fundamental interaction that determines the phase structure is the electromagnetic interaction. And the QCD phase diagram, it is a strongly interacting matter. So it is a conjecture phase diagram. Very little we know about it. This is the temperature versus baryon density is plotted. This is the simplest form of QCD phase diagram, which can be probed experimentally. And QCD predict that if you increase sufficiently high temperature or high baryon density, you might create a deconfined phase of quarks and gluons, which is quark-gluon plasma. At low temperature, you have a hadronic phase. Okay. Now, the QCD also predict, particularly lattice QCD, this temperature, the transition temperature here, like at 0 baryon density, is of the order of 165 MeV, which is huge. It's 10 to the power 12 Kelvin. If you compare the sun's core temperature, it is just 10 to the power 6 Kelvin. So we need to create that amount of energy, temperature in the lab, so that we can study the QCD phase diagram in laboratory. So my research goal is the experimental exploration of the QCD phase diagram using heavy ion collision. Okay. Now, this is a relativistic heavy ion collider where I am working. So this is situated in Brookhaven National Lab. So what happened, we have an ion source here, and ion source get accelerated, and we, let me see, and then we have a big accelerator here, which collide two ion beam. Here generally we use the gold ion. Ion means we strip up all electron from the atom and you get positively charged. And you can see there are 4 different experiment was there. All of them are actually not running, only the star experiment, this one is running where I am working. So what we do, this colliding energy we can vary. So maximum colliding energy, center of mass energy is 200 GeV in our case in this accelerator. So if we vary the colliding energy, we can actually vary the temperature and baryon density in this QCD phase diagram. So you can probe the QCD phase diagram by varying the colliding energy. So this is star collaboration. If you try to, this is the 1 kilometer is the diameter, and then if you look at the star collaboration, so there are 76 institutes from 14 different countries who are working, total 750 collaborators. So this is the map where the location of each institute is given. There are few from India. So you can see from this map that sun never sets in this collaboration. So now talking to my contribution of the research. So I will be presenting very selected result from this experiment where I have contributed. So first is properties of quark-gluon plasma. First we will see whether we have created the quark-gluon plasma and what is the properties. And second is what is the minimum energy needed to create a quark-gluon plasma. Okay. So first I will define a quantity called azimuthal anisotropy. So as I mentioned that we are colliding two nuclei. So let's say they are moving along z direction. One is going positive z, one is negative z. And when they collide in the transverse plane, then the xy plane, you can see there will be an overlap region. In this case is a non-zero impact parameter. So overlap region is anisotropic. It's an ellipse type shape, right? And when collision happens, the new particle will form and they will start interacting. And the interaction will give rise to pressure, and because of this anisotropy, the pressure gradient along x-axis will be more compared to the y-axis. So produced particle will feel more force along x-axis compared to the y. So if we plot the momentum distribution of the produced particle, we will see the anisotropy in the momentum phase also, right? And this azimuthal anisotropy is a measure of anisotropy in the momentum distribution, which can be measured if we decompose the produced particle azimuthal distribution in the Fourier series. And different Fourier coefficient will give you different order of anisotropy. Here we are interested in the elliptical shape. That is why we will talk about the second order Fourier coefficient that is called elliptic flow. Okay. Oh, it's got in. How? Is there any way I can switch to PDF? Could you do it quickly? Otherwise, it's very difficult. Okay. Oof. Okay. So this is the result. So we measured this V2 parameter or elliptic flow for different identified hadrons. So the left hand side is the non-strange hadrons, the proton and pion. Right hand side is the strange hadrons, the omega and phi. They are purely made up of strange quark. Then V2 is plotted as a function of transverse momentum. So what we see at the lower transverse momentum, the lighter particle like pion showing the higher V2 compared to the proton. Okay. And as you go to the intermediate PT, the proton showing the higher V2 compared to the pion. Similarly, we observe for strange hadron omega and phi. Omega is heavier, so it's showing the lower V2 compared to the phi, and then again it is showing higher V2 angle. So why I have chosen these two? So this is non-strange and strange, but this proton is a baryon, pi is a meson. So here omega is a baryon, phi is a meson. So in the lower PT, we see as a mass ordering, which can be explained by hydrodynamics evolution of quark-gluon plasma. But intermediate PT, we see there is a particle type dependent. So protons and omega, they both are baryon, although their mass is different. But if you compare the both axes, they are same almost. For pion and phi, they are meson, so their mass is different, but they are giving the same V2. So this particle type dependent actually can be explained by the hydronization of through the quark coalescence. So if there is no QGP, then there is no question of hydronization through the quark coalescence. So this particle type dependence or baryon meson separation, we can say this is the evidence for formation of quark-gluon plasma. Now further, I will show here same quantity for many different particles, strange and non-strange. Okay. So this y-axis is now V2 scaled by number of constituent quark. So this is 2 for meson, 3 for baryon. X-axis is transverse momentum scaled by constituent quark. And you see that intermediate PT, the baryon meson separation is gone, and all are showing the similar V2. This scaling can be further improved at the low PT as well if we plot this x-axis is the transverse kinetic energy divided by n cube. And you see the nice scaling. And this scaling is considered as evidence of collectivity among the constituent quarks. So here the hadrons we have selected are made of up, down and strange quarks. So we can say that this plot suggests that there is a collectivity among the up, down and strange quark. So we ask this question, what about the heavy charm quark? Do they also exhibit collective behavior or not? Charm quark mass is 1.3 GeV approximately, where the up down is 2 to 4 MeV. Okay. So we measure the V2 for D meson, which consists of a one charm quark and one light quark. And again we applied the same technique, the NCQ scaling plot, the V2 divided by NQ as a function of transverse kinetic energy scaled by NQ. And the blue data points are D0, and you can see they also follow the scaling. So this measurement, which is done at gold-gold collision 200 GeV, tells us that charm quarks also exhibit collective behavior. Okay. Now from the measurement of the charm quark D0 V2, we can extract the diffusion coefficient of the charm quark in the QGP. The diffusion coefficient means how quickly something dissolves in a liquid. For example, if you add some drop of ink in the water, how quickly it dissolves. Okay. So how do we measure the diffusion coefficient? So it is a combination of both theory and experiment, theoretical prediction and experimental measurement. So we take the help of the idea of this Brownian motion. You know that Brownian motion, the larger particle undergo random motion in a liquid. So here you can say that these black dots are light quarks that made up QGP, and the yellow dots are the few charm quarks, and they are undergoing the Brownian type of motion. So if we measure the collectivity of the D meson, we can extract the diffusion coefficient. Okay. So this is what I have shown here. So again I am showing the data of D0, D meson V2, and I am showing the comparison with two theoretical model calculation. This black one showing that charm quark V2 of D0 without assuming the diffusion of charm quark, and you can see clearly that is under predicting the data, it cannot explain. If we include the diffusion of charm quark and with the diffusion coefficient between 2 to 5, it can nicely explain the experimental data. And this predicted value or this extracted value 2 to 5 is also consistent with the predicted by the lattice QCD. Which, okay. Now the last topic I will discuss what is the minimum energy needed to create a QGP. So far I was discussing the result in gold-gold collision at 200 GeV. Okay. So here again, so we tried to look at the NCQ scaling plot. If scaling is hold, then the QGP is there. If there is a breaking of scaling, so there you can say that possibly no QGP. So in the star we have collected data starting from 200 GeV to 3 GeV, okay, by varying the colliding energy. So this is the 19.6 GeV. You can see there is a nice scaling, all particles showing the same after properly scaled by NQ, then 17.3 GeV, and up to 7.7 GeV you see there is nice scaling. Okay. So you can say up to 7.7 GeV there is evidence for formation of QGP, and below 4.5 GeV we see that the scaling breaks. Yeah. Although we are limited by the statistics, but still you can see here these are the, even this V2 become negative. So there is no scaling at this lower energy. And between 4.5 to 7.7 GeV there is a transition region which needs to be further explored. Okay, so let me summarize. So there is a evidence for formation of QGP for up to 7.7 GeV and above that, and we have seen that in QGP there is a collective behavior among the constituents of quarks, and the QGP signature disappear at 4.5 GeV. I will finish by showing the QCD phase diagram again. So our aim is to exploration of QCD phase diagram. So this temperature versus baryonic chemical potential plot, I have added many dots here. So starting from this 200 GeV to 3 GeV. So each dot corresponds to the different energy where the star has collecting data. So we are analyzing all this data to precisely measure the properties of QGP. So stay tuned for the new result. Thank you for your attention.
Thank you so much. Questions?
Phase diagram, yeah. So it was a prediction, but still now experimentally we are looking for it, but there is no concrete evidence that it is there. So if I just go back to, oh sorry. Yeah, so this QCD bed model predict that this transition is a first order phase transition, and lattice QCD predict that at 0 MeV is a crossover. So there must be some point where the first order phase transition ends. So this is known as the critical point, but experimentally it's not found yet. Yeah. So in STAR we have already submitted a paper. So there are some hints of deviation at 19.6 GeV from the non-critical model, but still we cannot say there's enough evidence for critical point. Yeah. So the upcoming experiment, the CBM, the Germany Fair facility, they might be useful to look for even higher baryon density, whether there is a.
So color superconductivity is not yet reached.
Yeah, using accelerator we cannot reach that much. Yeah.
Any further questions? Thank you then, Dr. Naseem.
Thank you.
Thanks. So the last lecture of this session is by Dr. Gaurav Sharma from IIT Hyderabad. He did his PhD from IMTech Chandigarh, and he's going to talk about evolutionary threads of myxobacterial flagella.
Hello. Great. Okay, so thank you very much, Academy, for inviting me to give a lecture, and thank you very much for this wonderful arrangement here. So today I will be talking about some of our recent work which we have been doing, entitled as Tracing the Evolutionary Threads of Myxobacterial Flagella. So I'm sure we are kind of getting delayed for the tea, but I will try to make it a little bit engaging so that you understand what we are doing here. So my lab usually works on sensing mechanisms. So this is knock, like we try to ask the bacteria that how they are sensing the environment, and that's what this story will go on. And Utkarsha has been leading this work, and she will be graduating this year on in the coming year. So we at IIT Hyderabad has two departments related to biology, biotechnology and biomedical engineering. In biotechnology there are several branches, and we do majorly big data biology and microbiology in our lab. And the main question which we have been trying to understand from our work is, I'm sure many of you are aware of DNA, proteins, and DNA proteins have sequences which can be computationally seen, as you can see here. And then these sequences turns into structures which are actually the functional unit of any particular protein, and these functions, they keep evolving. So we are trying to understand this whole dogma of sequence, structure, function and evolution, and to some extent most of our lab projects are revolving around these four things. The major focus area in my lab is on microbes. We do a lot of work with microbes in between. On SARS-CoV-2 also we did some work. Today my focus will be on the myxobacterial genomics. We also do a little bit of medicinal plant genomics and metagenomics. Again, here also we are staying with microbes only. We are trying to understand how plant and microbes are interacting. We are doing a lot of collaborations, and from last 2 years we are also developing several tools which is actually very fascinating to develop, because you can go in any kind of computational direction. These are some of our tools which we have recently made, and some of them are most of them are under review because we started last year only. In case you are interested, we do a little bit of a very off the research kind of work also. We have created one very fascinating tool, Google Scholar Lens, which if you will run on your Google Scholar profile, it will kind of bifurcate or multifurcate your Google Scholar data into authorships, and also create a new index which we are calling SH index. It's a new version of H index, and again this story will be out soon. I'm sure you will come to know about it. Okay, so coming to the main topic of this evening. So we work with myxobacteria. These are social microbes. They live in groups. What you are seeing here are fruiting bodies of myxobacteria, and I have been working on myxobacteria since my PhD, published so many papers, but still there are so many questions which are pending, and we are still looking into it. They are very unique because of several reasons. First is their unique taxonomy. They are majorly aerobic organisms, as here, but they evolved from anaerobes. So anaerobes means they don't need oxygen for their respiration, but these organisms have evolved to utilize oxygen. Second very important thing, at least for computational person like me, is they have a very large genome size, very large genome size in terms of bacteria. A bacteria is supposed to have like 3 to 5 MB genome on average. If you see, this is all the bacteria. Sorry, this is a little bit incoordinated. But yeah, if you see, they are all the bacterial genome size, and Myxobacteria lies on the top of it, which means that they have the largest genome size. Even the largest genome has been sequenced by me during my PhD. So, and because of this, they have and because they are social organisms, they have a very complex signal transduction system. Means they have a very complex sensing mechanisms which allow them to sense the environment. Now, the third most important thing about them is that obviously they have a very complex physiology. They have a very large genome size, so they encode a lot of proteins, and many of these proteins are involved in their social behavior, their gliding, their fruiting body. They make like so many secondary metabolites which are antibiotics, which I will discuss a little bit. They degrade so many biomolecules, and they are very slow growing. So many of these questions, many of these physiological parameters are very fascinating for a computational person also. So another very important thing about these organisms, which is less explored as of now, is they make they make the largest number of secondary metabolites per organism. So if you see, this is the distribution of all the secondary metabolites. So secondary metabolites, for those people who don't know, secondary metabolites are actually the antibiotic molecules, which when they are within the genome, we call them secondary metabolite, but when they are expressed and come out of the bacteria or secreted out, they usually are very good antibiotic molecules. And if you see here, these are the Myxobacteria, which you can see here, and they make the largest number of secondary metabolites, at least in the whole bacterial kingdom, on median scale. Even if you see, one of the largest secondary metabolite producer is Streptomyces, which has been worked on a lot, as you can see by the dots. They make, most of these Myxobacteria, they make more than Streptomyces secondary metabolites. So very fascinating organism. But so in the last several years, while working with these genomes, we have come to several type of conclusions and several type of theories. So means maybe many of you will recognize this organism. Okay, Archaeopteryx. Okay, so it's a organism, Archaeopteryx, which we usually say, and we have found it as only fossils. Okay, that it was kind of a connecting link between reptiles and aves. Aves means birds. So it has features of reptiles and birds. Okay, which is very fascinating. So they are, in evolutionary biology, we call them missing links or connecting links. So we have found similar kind of things. If you see, these are the bacteria and these are fungi. Okay, so these Myxobacteria, which we usually work on, they have, obviously they are rod shaped, but they make spores similar to how fungi makes these in sporangials. Okay, so these are sporangials of Myxo, which is almost similar to fungi. So sometimes Myxobacteria are also known as kind of a connecting link between bacteria and fungi. But we are going one step further. So these are all our organisms, if you see. So these are Myxobacteria. Okay, and if you see, most of them are 9 MB. They are aerobic, and they have 70% GC content. And their ancestors, which we are saying earlier, they are delta proteobacteria, which are very low genome size, 5 MB. They are strictly anaerobe, and they have a GC content of 45%. So what we have found in the last several years, that these three organisms are kind of connecting link organism between this and this, because they share many properties with each other. So now if you see, their genome size is almost equal to the ancestor. Some of them, 2 of them at least, they are strictly anaerobe, similar to the delta, and one of them have like almost equal GC percentage as delta proteobacteria, and obviously many of them share the similar properties with Myxobacteria. So based on this, we are trying to convey that these are connecting link organisms, these three organisms, and they can tell us a lot about the evolution of these Myxobacteria in a general perspective. Okay. So as I said, that we have been working on several of these things. We have sequenced them, cultured them, sequenced them in our lab from last several years, working on several of these directions. Today I will just talk about signal transduction gliding motility. So just to introduce you quickly to the motility, most of the organisms are, most of the bacteria are motile, many of them are non-motile also, where they take support of other organisms to move, or they take help of the host. Okay. But the moving organisms they usually move, the bacteria, they usually move either with flagella. So as you can see here, the thread-like structure, and that's what we call flagella. And sometimes they move by pili. Pili are a small thread-like organism, but very shorter than flagella. And many organisms do move by focal adhesion complexes, and some of them just slide. Okay. So out of these all 5 kind of motility patterns, Myxobacteria depict gliding and twitching. Okay. So they do either gliding or twitching. So just remember that, which also conveys, means I am just trying to give you some preliminary data, that they don't have flagella. Okay. Means Myxobacteria are not known to have flagella. You will ask that why the title has flagella. So we will come to that later. Okay. Now most of these motility, they are supported by sensing. So a bacteria who is living in this environment, it will sense the environment. If there is a chemoattractant, it will move towards it. If there is a repellent, it will move away from it. So they do this using signal transduction system, as you can see here. These are the overall bacterial signal transduction system, which can be like one component, which are transcription regulator, where there is only one protein. In 2 component system, there are 2 proteins, sensor kinase, which will sense the signal, as you can see here, and respond via this response regulator to the target gene, activation or repression. Now this is a complicated 2 component system, where the signal is received by this chemoreceptor protein, which we call MCP protein. It sends the signal from outside, like either by this ligand binding domain, and then it will send it to key A, which is similar to a sensor kinase, and then it will send the signal to key Y, and this key Y will send the signal to all the functions. It can be flagellar motility, type 4 pili motility, or so many functions which bacteria can do using these chemosensory systems. So remember that chemosensory systems are one of the most complex sensing mechanism system, at least in the bacteria. Now we have developed some methodology to identify these systems, and if you see, this is E. coli. So E. coli has this chemosensory system, MOT-A, key A, key R, MCP, and TAR protein, and nearby you can see these are flagellar genes. Okay. So the blue ones are the flagellar genes, and the system is kind of go on. So now if you see, E. coli has one chemosensory system. E. coli is a small genome, 4 MB. Similarly, Bacillus is also 1 MB genome. But if you see Myxococcus xanthus, which is a 9 MB genome, it has 8 chemosensory systems, which is the largest in the bacterial kingdom. And even if you see Pseudomonas or Vibrio, which are almost similar to the E. coli, they have 3 or 4, which is a large number for a small organism. So what I have done earlier, we have identified all these chemosensory system across Myxobacteria, and we have characterized them. We have identified almost there can be 14 type of chemosensory systems within the bacteria, within these organisms, and we have also characterized their function using some in silico analysis, and it has been earlier published. Again, we use a lot of, as a computational biologist, we use a lot of phylogeny. In case phylogeny is a difficult word for you, phylogeny, we try to take like similar type of sequences, try to cluster them, and then demarcate each cluster separately. So it's basically similarity based clustering, and if you see, each cluster is kind of making one clade. So if you see this one is one single cluster, key 3. If you see this one is another cluster, key 1. So based on this phylogeny, we can easily classify these kind of systems. So what happened recently, means a few like last year also, we were exploring about this, and we found that there is, so this is our overall classification of chemosensory systems within Myxobacteria, and when we were looking at it, we found that these 2 systems, ECSS2 and ECSS3, they are only present in these 2 organisms, and maybe along with this one organism from here, which is very fascinating because this is only present in AD Andromyxobacter, which is our one of the connecting link organism, as I mentioned earlier. When we look into the phylogeny, you will see that these connecting link organisms are making a very separate clade or group as compared to all other Myxobacteria, which means that they have a different kind of features and different kind of physiology, even different kind of genome within them. So when we look into this cluster, we found that ECSS3 and ECSS2 are present together, and upstream of it and downstream of it, we have full-fledged flagellar cluster. Okay. So remember that how genome works, that if there are genes, which are making some particular type of protein present in the genome, usually it means that it will, it should work, it should express, and it should give some function. Okay. It is possible that some of the key components might be missing, and in that way it is not functioning as it should. So what we realized that in Enteromyxobacter at least, they have full flagellar system. So it was very fascinating that, okay, why these organisms have flagellar system. So we looked into, in case, just to quickly give you some heads up, that flagellar system is a very big macro machine. It's made up of like almost 30 to 50 proteins, and they work based on the rotation by these MOT A, MOT B proteins here. Okay. And these KY, which I was discussing in the chemosensory system, this KY, they will regulate FLIM protein here, which is here, FLIM protein, and decide that flagella should rotate counterclockwise or clockwise. Okay. So based on chemoattractant, if there is a chemoattractant, the flagella will do counterclockwise motion, which will move forward. If it's a repellent, it will do clockwise motion, which will do reverse motion. Okay. So we did phylogeny of again all those proteins in all the organisms, and we found that this particular system, which is involved in flagella, it is making one separate cluster, as you can see here. That's what we expected, and as you can see, it is only present in Enteromyxobacteriaceae and Labilithraceae and not anywhere else. And as you can see, all the clusters are very well demarcated, F10 separate, F5 separate, F8 separate. We also looked into flagellar gene orthologs, and we found that only in these two group of organisms we have flagellar genes, and in rest of them the genes are completely absent. So the question is that Myxobacteria don't have flagella, they do gliding motility via pili or focal adhesion molecules. So what is happening in these connecting links, and how these connecting links have these full-fledged system. So we expanded our analysis first to the MAGs. MAGs are metagenomes from very niche areas like very deep sea or untouched habitats, or even like local environment like this. So we found that many of those deep sea ocean MAGs, they also have this particular cluster. As you can see, this is F7 cluster, and now F7 cluster has Enteromyxobacter plus these many different type of MAGs, which means that even in those MAGs this system is present. Okay. We looked into all those MAGs, and we found that yes, the chemosensory system proteins are in between, and flagellar genes are present on upstream and downstream, suggesting that they have those systems. So we again generated another phylogeny and mapped all these proteins, and if you see, the colored ones are MAGs, and these ones, the groups which I have put rectangles, they are the Enteromyxobacter connecting links, and if you see, they all have flagellar systems. Now another thing is that this system is F7 type, and this F7 system is only present in these rectangles. And when you see the sensing protein or MCP protein, only this particular protein 36H, which does help in flagellar motility, it is also only present in these rectangles, which suggests that these organisms have the sensing protein, they have the flagella, and they have the chemosensory system, and all of these three machines are working together to move via flagella in that particular environment, because at one point of time these ancestors or these connecting links, they must be residing or living in an environment where flagella was required, and now because they are living in soil, flagella is not required. So that's why they have lose these flagella from their system along with chemosensory system. So a very big machine or two very big machines they have lost in their life cycle. So this is our final proposing model, that these are the ancestors which has the flagella and the chemosensory system and the MCP protein, all three. But in due course of time, only the connecting link organisms which we are suggesting, they have these partial, or you can say 90% or 95% of the flagellar genes and chemosensory genes, but rest of the isolates which are very well growing in the environment, soil environment, they have lost these three specific systems. So this is a manuscript under preparation, and we are trying to communicate it soon. So with this, I would like to thank the whole lab who has been working with me, all the people. They are all working on very different aspects of myxobacteria and some other aspects of Vibrio, SARS-CoV-2 and tool making. And we are supported by Inspire and DST, yeah, ANRF also now. Yeah, thank you very much. Yes, sir? No, I'm here. So, yeah.
So, nice talk. Any questions? Yeah.
So, these are kind of a connection between unicellular and multicellular stuff. I mean, do they have quorum sensing and things like that? I mean,
yeah. So very good question, ideally, because means we didn't discuss it, or I have hidden that slide of multicellularity. So these so we are multicellular organism. They depict multicellular behavior. So they are social microbes. So they do like swarming as a group. So if and they are very slow growing organisms. So they just keep swarming like this. So if you see on plate, they will keep growing like this. Even if they have to do predation of other small organisms, they will, swarm like this and try to engulf them. So yeah, they depict like this kind of behavior. We are not studying them, at least in this study, but yeah, that's kind of a step forward.
So do they have quorum sensing type of signaling mechanism?
Yeah, so the quorum sensing comes as a very preliminary kind of sensing, ideally. So they don't have that too many. So the one component system is kind of low dominant, two component system are very high. So their major signaling is via two component system. So if you see some other organism, let's say Vibrio do a lot of quorum sensing along with two component system also.
So when they receive signal, they do it collectively.
Yes,
that's what you are saying.
Collectively via two component or chemosensory or these kind of behaviors.
Thank you.
Any more questions? So I have, if there's any more questions.
Yeah, so there's RNA-seq data also for these.
So we are trying to find it. So the problem is like the overall problem why myxobacteria are not becoming very famous, similar to Streptomyces, is they are very slow growing. Very slow growing means you will not see the growth. You will see growth after 10 days or 7 days or 10 days. So in that time, the contamination and all those things will start jumping up. So the only organism for which we have a lot of data, or for which the molecular genetics is very well adapted, is Myxococcus xanthus. So for that we have a lot of data, RNA-seq also. But at least for these connecting link organism, I think overall there are 5 or 10 papers. So we don't have that much prevalence. Yeah. Yes. So right now, so this is a little bit old data. Old data means like 2-month-old data. So this has 81 complete genomes, and I think 50 metagenomes. But in the latest version, which my student is working, we have taken the whole data set which is available for metagenome, which is like almost 5,000 metagenomes, and around 81. The genome wise it's same, but metagenomes we have increased.
So two curious questions.
Yes.
One of the thing is the switch from anaerobic to aerobic. So there would be a big metabolic switch. So did you have a chance to look at the extra part of the genome which does not map to the ancestral genome? Does it actually have those kinds of functions in them?
Yeah.
And where would that genome would have come from? Because it would not be by mutation, so it would be some horizontal gene transfer. So did you get a chance to see where that extra, what is that extra thing contributing to?
No, that's a very, very fascinating question, because ideally that is the main question of Utkarsha, which she is working on, but she tumbled on this story, and this question is kind of like getting a little bit lagged. But so what is happening with Mixo, they have only 15% genes coming from ancestor. Rest 85% is coming from different clades. Why they have been accumulating that means we don't have an answer right now. But even if you see, let's say this kind of this flagellar system. So this flagellar system, we are trying to find out that okay, it came from like let's say some other group of organism. So they didn't have it earlier. Okay, even so it's kind of becoming why they have gained this much genome. That is the broadest question which we have. For that, the main first point is that they have been accumulating it extensively and doing duplication and neo-functionalization. So they have been gaining, duplicating and making new function for those proteins. Why they are doing it? That is no, that I also don't know.
Could the alternative be that they really are not the connecting link because they have a large genome from some other and they have actually acquired the other part of the genome from the bacteria? Meaning, if you flip it around, because if the bulk of the genome behavior is different, then could the part which you're dealing with is an acquired part?
Yes. No, that's a good point. So now if you think of it, only one clade of Andromyxobacter has a small genome. All others are kind of very big genomes, like ranges from 9 to 16, all the other parts. So it looks, means again, like gene gain and loss is kind of very relative term. Someone can say they are gaining, someone can say they are losing, but it looks like that the others have gained, and that's how they have flourished or they have become like this huge.
Okay. If there's a question there.
Gene transfer, like it has a very big gene size. So is it like acquired a lot of genes due to horizontal gene transfer or something like that?
So when any bacteria acquire gene or multiple genes or big cluster from other organism, that is horizontal gene transfer. So whatever we are saying that 70% or 75% genome is coming from outside, it means it's coming via horizontal gene transfer.
Okay. So is there any evidence that from which organism it acquired this much of genome or something like that?
So means evidence wise we have the data, not in this at least, but yeah, we have the data. Means phylogeny is a very good indicator in that manner.
Yes.
And some of those phylogenies are very clean phylogeny, where you can directly see that we have this organism and the nearest organism group is very far away in the taxonomy. So something like if we say human got something from Neanderthal will be like very close by, but like from fish. Okay, so that kind of far away.
Okay. Thank you.
So I think we come to the end of the session. Thank you so much, and thanks the audience for being there. I guess we'll break for tea.